Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies following ancient light on its unhurried path through time. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Tell me if you'd like where you're listening from and what time the stars rise where you are tonight. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. Far from Earth, the planet Mars drifts in silence. Around it, a handful of machines glide in slow, patient arcs. They have been circling for years, mapping craters, measuring dust, listening to faint whispers of the solar wind. But on this particular night in early October 2025, they have turned their eyes away from the red world below. They're all pointing outward, towards something stranger, something moving swiftly through the darkness beyond Mars. The object has a name that sounds almost mythic: Three-Eye Atlas. The third interstellar visitor ever confirmed. A body from another star system, wandering into our own for the briefest of moments before vanishing again into interstellar space. It passed within 29 million kilometers of Mars, a distance that, in cosmic terms, feels close enough to touch. From those orbiters, Mars Reconnaissance, ExoMars Trace Gas Orbiter, Mars Express, images begin to stream back across the void. Each instrument, each sensor, collecting light that has crossed tens of millions of kilometers, all in the hope of resolving the smallest hint of detail. One pixel could hold an answer, or another question. On Earth, we watch. Astronomers gather in control rooms lit only by the soft glow of monitors. The object's outgassing rate has been measured at 150 kilograms per second, an invisible storm of carbon dioxide and dust, pouring into space with no sign of recoil. That by itself is almost impossible. When a comet vents gas, Newton's law demands reaction, push and counterpush. Yet here, the balance seems perfect. The plume expands, but the motion doesn't shift. It's like watching a cannon fire without a single tremor. Even at this early moment, the numbers are troubling. To resist such force, the object must be heavy, far heavier than any comet of similar size. The early estimates place its mass around 33 billion tons, compressed into a shape only a few kilometers wide. That would make it a mountain of material moving through the solar wind, dense enough to shrug off the breath of its own eruption. No one expected the third interstellar object we'd ever find to be the strangest yet. The first, Oumuamua, had been a sliver, tumbling and fading, its brightness flickering like a blade catching light. The second, Borisov, looked ordinary, icy, familiar, behaving as comets do. But this one, Atlas, refuses to obey the script. Even the images from the Mars orbiters, though distant and faint, carry a certain gravity. The high-risk camera on the Mars Reconnaissance Orbiter, designed to photograph Martian cliffs and dunes, has been repurposed for this one task. It captures frames of the blackness around Mars, searching for a streak, a glow, anything. Each exposure is a small miracle of alignment, aimed at a moving target that doesn't belong to our sun. What fascinates scientists most is not only that we can see such a visitor, but that we can time its arrival so precisely. Until recently, the odds of catching one in transit were nearly impossible. Space is vast, the windows of detection are tiny, yet our technology is sharpened to a point where we can spot these brief intrusions from other stars like sparks drifting through the dark sea. Three-Eye Atlas may have come from an unknown system, or perhaps from no system at all. A wanderer thrown from its birthplace billions of years ago. As it moves, it carries stories in its chemistry, in the ratios of its gases, in the alignment of its path. The orbit it follows is steeped in improbability, skimming close to the plane of our planets as though it had chosen a lane meant for us. At this moment, Mars provides a vantage we may never have again. The geometry of orbits has aligned perfectly. The red planet, the sun, and this mysterious object all caught in a brief cosmic chord. For a few days, humanity's machines are close enough to glimpse details that Earth's telescopes could not. The difference between their images and those from Hubble is staggering, 20 times finer in resolution, enough to reveal texture if texture exists. We often forget that space exploration is as much about timing as distance. The instruments circling Mars were never meant to look outward. Their cameras were built to study terrain and atmosphere, not to chase interstellar ghosts. Yet they are all that we have in this moment. Their eyes, turned sideways into the void, might record something no telescope on Earth could ever see. You can imagine the stillness inside those spacecraft. No sound, no vibration. Just the faint ticking of internal heaters, the hum of electronics, the pulse of data transmitted through invisible waves. From that silence, a portrait begins to form, a faint halo, a bright core, an enigma set against the velvet backdrop of the sun's scattered light. For those who study it, this is not only a chance to learn about a visitor, it's a test of how we listen to the universe. Every photon counts. Every faint spectrum line could reveal temperature, chemistry, motion. From a handful of numbers, we try to build a story of matter older than our solar system, shaped by conditions that might no longer exist anywhere nearby. There's something humbling in that. To watch our machines stretch their gaze beyond their design, to capture something ancient and indifferent. The data will take days, maybe weeks to reach full clarity. Engineers will clean the noise, adjust calibrations, compare overlapping images. The answers will come slowly, in the way all deep things reveal themselves. Somewhere in the telemetry, hidden within strings of numbers and error margins, may lie a glimpse of what 3i Atlas really is, a fragment of another world, a relic of a system long dissolved into starlight, or something that refuses to be described by what we already know. As we wait for that data to unfold, the image of Mars itself seems changed. Its orbit becomes a platform for observation, a quiet balcony overlooking interstellar space. The thin atmosphere glows faintly in the scattered light of the sun, and far beyond, a tiny point of motion slips across the darkness, a reminder that even the most familiar planets are just stepping stones in a greater cosmic river. We're watching, not for spectacle, but for understanding. The light that left 3i Atlas minutes ago is being caught now by sensors built by human hands, carried across millions of kilometers. It arrives as bits of information, yet within it may be something profound, a signal from another corner of creation, passing through our neighborhood before vanishing again into the long night. 3i Atlas is, by every known measure, a paradox adrift in sunlight. Its mass, 33 billion tons, is squeezed into a span of only a few kilometers. For context, that means more matter than the entire population of Mount Everest's peaks, pressed into the volume of a single mountain, drifting freely through the solar system. When astronomers speak of improbabilities, they usually mean statistics, not disbelief. Yet this number made even the calmest researchers stare for a long time at their screens before daring to accept it. In most simulations, interstellar debris follows a clear pattern. The universe, after all, is a patient sculptor. When stars form, their disks scatter fragments of rock and ice into surrounding space. Small pieces vastly outnumber large ones, a handful of mountain-sized fragments for every billion pebbles, perhaps even fewer. When the first interstellar object, Oumuamua, passed by in 2017, its small size fit that rule perfectly. Less than 200 meters across, a shard shaped like a skipping stone. The second, Borisov, was slightly larger but still ordinary, its tail whispering of simple ices and dust. The third should have been smaller still. But 3 Atlas is not small. It is, at minimum, 5 kilometers wide, possibly more. That makes it 1,000 to 1,000,000 times more massive than anything we should have found at this stage of discovery. If the galaxy truly obeyed our equations, this object should have been nearly impossible to stumble upon. Finding something this large so quickly implies one of two things. Either our models are wrong, or chance itself has a sense of mischief. Imagine the Milky Way as a sea of invisible currents, gravitational waves and stellar winds. Debris from countless ancient collisions drifts through that sea. Every so often a fragment crosses paths with our sun. It's a lottery we've just begun to play, and already the jackpot seems too high to be credible. For scientists, such odds suggest that our assumptions about the galaxy's debris field might be deeply flawed. Perhaps it's not sparse and quiet, but filled with hidden travellers, dark bodies moving between the stars, too faint to see until one happens to drift into the light. That possibility carries its own quiet awe. We have long imagined interstellar space as mostly empty, a gulf between islands of creation. But if Atlas is representative, the truth may be stranger. The void could be crowded, not with life, but with relics, ancient remnants of formation, wandering through billions of years like slow meteors across eternity. Still, some wonder whether this object truly belongs in the category of natural wanderers at all. The mass discrepancy is not just statistical. It suggests that something about its density, its structure, or its origin is outside our experience. A typical comet is a porous mixture of ice and dust, its bulk light enough to crumble under a hammer's tap. Atlas seems different, compact, almost metallic in its resilience. When it vents gas, it barely flinches. That resistance requires extraordinary mass or a construction we've never seen in nature. The calculations are straightforward but haunting. A comet's outgassing, even at modest levels, should nudge its path ever so slightly. Over days and weeks, that push accumulates, altering its orbit. Astronomers track such shifts with precision instruments, adjusting models until the math fits reality. But for Atlas, the deviation is nearly zero. It moves as if anchored to the geometry of space itself. To absorb that much thrust without measurable motion, its interior must be astonishingly dense. Perhaps iron, perhaps something heavier. The densest natural bodies of comparable size are asteroids rich in metal, yet those do not behave like comets. They do not outgaze. They do not glow. Atlas combines contradictions like a riddle carved into light. In physics, contradictions are invitations. When equations break, new knowledge waits at the fracture line. Yet this one fractures in several places at once, too massive for comfort, too still for its violence, too bright for its distance, too cold for its chemistry. The result is a portrait of an object that should not exist and yet undeniably does. The discovery has forced a re-evaluation of what we consider possible in interstellar formation. Perhaps some stellar systems, especially those born in dense clusters, eject larger remnants than we imagined, chunks of planets or moons flung outward by gravitational tides. If that's true, the Milky Way may be filled with fragments of shattered worlds, each carrying traces of their lost stars. Atlas could be one such relic, a planetary core encased in ice, still bearing the mineral scars of its origin. Others propose more exotic ideas. Maybe the density isn't real. Maybe what we see as mass is an illusion created by geometry, an irregular shape reflecting sunlight in ways that trick our calculations. Light curves can be deceiving. A flattened body or one covered in bright reflective ice could appear larger or heavier than it truly is. Even so, the numbers strain to agree. There's also the uncomfortable truth that every discovery like this revises the previous two. Oumuamua forced scientists to confront non-gravitational accelerations with no clear source. Borisov restored normalcy for a while, and now Atlas has reopened the wound. 3 data points, 3 distinct behaviours, too few to chart a pattern, too many to dismiss. In science, it's rare for something to be both visible and mysterious. We usually struggle with one or the other. Either it hides from detection, or it yields to explanation. Atlas resists both extremes. It is bright enough to study, yet remains opaque to understanding. From a storytelling perspective, that makes it a mirror. Humanity's curiosity is reflected in this drifting stone, our questions orbiting around it as surely as our probes around Mars. Why is it so large? What forged it? What kind of cosmic weather shapes an object capable of breaking our rules? Perhaps the answer lies not in the object itself, but in our limited perspective. We are a young species with brief windows of observation. The galaxy has been forming and dissolving structures for 13 billion years. It's possible that phenomena common in the distant past have simply faded from memory, leaving us unprepared when they reappear. Atlas may be an echo of those ancient processes, a survivor from an era when stars were crowded and gravity sculpted matter into strange, dense forms. In that sense, every interstellar object is a messenger from a forgotten chapter of creation. Each carries within it the signature of the physical laws as they once were, perhaps only subtly different from ours, perhaps entirely alien in their chemistry. For now, Atlas drifts between Mars and the Sun, its tail invisible in the glare, its secrets buried under kilometers of ice and metal. But even without seeing the surface, we can feel its presence in the equations, in the tremor of data that refuses to align. It reminds us that the universe is not a solved puzzle. It is an open sky full of unspoken riddles. And as we watch this massive traveller sweep past Mars, we're reminded of how fragile our understanding is, how even after centuries of studying comets and planets, one silent visitor can arrive and rewrite what we thought we knew about how the cosmos builds and scatters its worlds. To know something in the dark, we begin with light. Every measurement of 3i Atlas starts as a photon captured by a mirror, split by a prism, turned into numbers. Yet the deeper scientists looked, the more those numbers argued with one another. Its size, such a simple question, became a moving target. Early estimates made when the object was far beyond Mars suggested it might be 20 kilometers across. Then later observations, refined by the Vera Rubin Observatory, halved that, then halved again. 5 kilometers, perhaps even less. A spread so wide it spans the distance between a city and a single hill. The object seemed to shrink with every improved measurement, as though distance itself were peeling layers away. This is the strange humility of astronomy. Almost nothing we study can be touched. We measure shadows, reflections, absences. The brightness of 3i Atlas is translated into diameter through the quiet language of albedo, the fraction of sunlight reflected by a surface. A shiny surface can look large, a dark one small. Change one assumption, and the object's size doubles or vanishes. Astronomers compare the situation to estimating the shape of a bird by the pattern of its echo. You hear a sound in the dark, a brief reflection of a signal you sent, and from it you must deduce not only distance but form, colour, texture. The uncertainty becomes part of the discovery. The instruments that first caught sight of Atlas were working at their limits. The Hubble Space Telescope, orbiting high above Earth's atmosphere, recorded the faint smear of a coma, a halo of gas and dust surrounding the nucleus. But at hundreds of millions of kilometres, even Hubble's precision could resolve little more than a bright point blurred by motion. The James Webb Space Telescope contributed spectroscopic data, analysing the wavelengths of light to identify molecules, but it too could only infer, not see. When you picture Webb turning its golden mirrors toward that moving glimmer, imagine how faint it must be. A visitor from another star smaller than the smallest moon, reflecting sunlight across hundreds of millions of kilometres. Each photon it sends carries the story of its surface, a mixture of ancient ice, carbon dioxide, and something else not yet named. Those photons arrive at Webb's instruments, are separated by wavelength, and plotted as peaks and troughs. From those graphs, scientists extract meaning the way a musician might read the emotion behind a melody. As the data came in, a subtle rhythm appeared. The object was brighter than expected for its distance, but not consistent in that brightness across time. Yet the variations didn't align with rotation, as one might expect from a tumbling rock. They were erratic, almost like the object's surface was venting irregularly, releasing small jets of gas that brightened its halo. Each event, perhaps, a little sigh of ice turning into vapour under the sun's growing warmth. Still, even accounting for these changes, the brightness was too high. Something about the dust or gas surrounding 3i Atlas made it unusually reflective. Its coma shimmered like powdered glass, scattering sunlight with a finesse that defied the typical dullness of cometary dust. If the material were metallic, or layered with fine crystals, it could explain the effect, but that would also make it denser, and we return again to that impossible mass. In astronomy, the line between observation and interpretation is delicate. When a telescope records a light curve, a plot of brightness over time, the human mind translates that pattern into story. Peaks become eruptions, troughs become shadows, but sometimes the light curve lies. Sometimes the story we think we see is just a trick of geometry, the object rotating edge-on, or its reflective patching distorting the numbers. To reduce such ambiguity, astronomers use parallax. Two telescopes, widely separated, observe the same targets simultaneously. The slight difference in perspective allows them to triangulate distance. With Mars orbiters observing in parallel with Earth-based telescopes, that baseline expands enormously. For a brief moment, humanity had two vantage points separated by tens of millions of kilometers, enough to reconstruct depth, to refine speed, to measure how light interacts with shape. Those measurements narrowed the estimates but did not eliminate uncertainty. Whether Atlas is 20 kilometers across or 4, it remains an outlier. If large, its mass upends our expectations. If small, its activity does. A body less than a kilometer wide releasing that much gas per second would have to be evaporating from within, heated not just by sunlight, but by something internal. Sometimes scientists speak of impossible data, not as disbelief, but as fatigue. When every correction still fails to align with a model, they start to suspect the model itself. The distances involved here are so vast that even the speed of light feels slow. Signals from Mars orbiters take minutes to reach us, then hours of decoding before they reveal anything useful. During that silence, Atlas keeps moving, keeps venting, keeps defying expectation. Yet this is the beauty of patient observation. The sky does not hurry. It waits for us to notice patterns hidden in the noise. Over weeks, as new data arrived, the picture of Atlas grew both sharper and stranger. Its core might be smaller than we thought, its brightness higher, its mass paradoxically constant, like a riddle tightening its phrasing. All through this process, the instruments whisper their limits. Every image, no matter how high the resolution, blurs at the edges. Every spectrum hums with noise. To know the universe at this level is to live with uncertainty not as an error, but as a companion. The shadows remind us we're still learning to see. We might imagine standing on a quiet plain beneath the night sky, looking up and realizing that the light from that visitor is already a memory, minutes old, travelling through the solar wind, shaped by forces that we can only simulate in our minds. To measure that memory, to argue over its meaning, is to participate in the oldest human tradition, wondering what the heavens are trying to say. Even if Atlas remains a blur for now, the effort to define it brings precision to everything else. Instruments recalibrated for this study will serve for decades. Algorithms trained on its data will detect new wanderers, perhaps dozens in the coming years. Each new detection will shrink the uncertainty pixel by pixel, until our picture of the interstellar sea becomes clear enough to navigate. For now, though, we rest in the unknown, a traveller of uncertain size gleaming faintly beyond Mars, challenging our understanding of scale and distance. Its true form remains hidden, like a shape behind frosted glass, visible yet not. And perhaps that's fitting. The universe rarely reveals its truths all at once. It offers glimpses, moments of clarity that fade as quickly as they arrive. So we wait, patient as the telescopes themselves, letting the light come to us. The first photographs to catch 3I Atlas in motion showed something no one expected, a streak of brightness pointing toward the sun instead of away from it. In most comets, solar radiation pushes the dust and gas outward, forming a tail that streams opposite the sunlight. It is one of the most predictable signatures in planetary science, the same physics that gives us the sweeping shapes of Halley's Comet or Hale-Bopp. But in these images, the geometry was reversed. A narrow jet of light, long and slender, appeared to lean sunward, as though the comet were exhaling toward the very furnace that should have been pushing it back. The idea itself sounds contradictory, but the data were consistent. The jet was 10 times longer than it was wide, luminous, and persistent across multiple days of observation. It brightened when the object turned its sunlit face toward us, then held steady while the faint, more typical tail barely began to form. To explain this, astronomers turn to physics they know well. Comets vent gas when solar heat strikes volatile ices: carbon dioxide, carbon monoxide, water. These gases expand rapidly, carrying dust with them. Usually the solar wind, a thin, continuous flow of charged particles from the sun, sweeps that material outward. But if outgassing occurs on the sunward side with enough force, the ejected material can reflect light directly back toward the sun before being deflected. That is the standard model, and yet, in Atlas, the jet began long before such heating should have been strong enough to awaken the ice. At that distance, nearly 3 astronomical units when first observed, ordinary comets remain quiet, their surfaces too cold for significant sublimation. But 3 Atlas was active, already venting with a steadiness that felt premature. Something inside it was warmer, or something about its composition allowed it to release gases at temperatures where most ices still sleep. You can imagine the surprise. The first team thought the image might be flawed, an artifact of processing, maybe a smudge on the sensor. Yet other observatories confirmed it. The forward jet existed. For those who study comets, it felt like seeing fire flow uphill. In every cometary event, geometry plays a role. Sunlight, angle of observation, rotation of the nucleus, each influences how a tail appears. But when multiple telescopes across the world and in orbit record the same impossible orientation, chance geometry fades as an excuse. The object truly was venting toward the sun, a behaviour that had no place in any catalogue. Scientists began to describe the object in 2 layers. There was the visible body, reflecting sunlight in gentle arcs, and beneath it, an invisible engine, some process controlling the release of material. The jet's stability over weeks suggested not a chaotic eruption, but a persistent vent, like a geyser repeating its rhythm. If Atlas rotated, the vent should sweep, creating fluctuations in brightness. Yet the data showed near-perfect consistency. Either the object wasn't rotating at all, or the venting was symmetric enough to cancel any visible flicker. In that stillness lies mystery. For a jet to remain perfectly aligned while the body rotates requires constant adjustment, some feedback mechanism maintaining balance, but comets have no mechanisms, only physics, unless of course this one does. There are natural explanations still on the table. The jet might not be a physical plume at all, but a reflection phenomenon, a patch of unusually reflective dust oriented just so. Yet that would require improbable precision over weeks, or perhaps the material ejected sunward is metallic or carbon-rich, scattering sunlight differently. Scientists compared the data to that from other outgassing comets, searching for any precedent. None fit cleanly. Meanwhile, the gas composition began to add more questions. When light passes through a comet's coma, Each molecule absorbs and emits at characteristic wavelengths, producing a spectral fingerprint. Carbon dioxide dominates at some lines, water at others. The brightness of Atlas's jet matched the signature of carbon dioxide rather than water vapour, an unusual trait at such distance. It was as if the object's surface was composed not of typical ice, but of something that evaporates earlier, a frost born in colder, more distant origins. The forward jet complicates even simple things like predicting the orbit. In celestial mechanics, we assume outgassing pushes comets slightly off course, a small acceleration measurable over time. For Atlas, the force of the jet pointed inward, toward the sun, opposite what we expect. If it exerted real thrust, it would alter the object's trajectory in the wrong direction, pulling it closer rather than nudging it away. Yet tracking showed no such deviation. That leaves one possibility that chills and fascinates astronomers alike. The jet exists, but it does not push. A phenomenon with visible energy output and no momentum transfer, something we cannot yet model. In the quiet world of astrophysics, where precision is sacred, such contradictions echo loudly. For months, models were revised, equations rewritten, hypotheses stacked upon one another like scaffolding around an invisible structure. Some suggested a hollow core allowing gases to flow evenly from both poles, cancelling momentum. Others imagined an internal heat source distributing energy uniformly, so the jet was optical, not mechanical, a reflection of deeper luminescence. None of it could be proved, but none of it could be dismissed either. If you close your eyes for a moment, you can picture it. A small dark sphere against the black, sunlight glancing off its trailing dust, and a single thin beam of gas glowing softly, not outward, but inward. A comet defying every instinct of motion, releasing its breath toward the star that warms it. It's hard not to feel a kind of reverence for such elegance. The cosmos rarely violates its own symmetry so openly, and yet, as we've learned, the universe seems willing to bend its own rules when we look closely enough. In the history of comet studies, few objects have carried such aesthetic strangeness. The Great Comet of 1577 showed two tails at odd angles, baffling early astronomers. Comet 29P bursts repeatedly from deep within, producing jets for reasons still debated, but none have shown an enduring sunward plume like Atlas. When the data first circulated among international teams, one researcher called it a gesture of defiance written in gas. That poetic phrase found its way into conference notes and quietly stayed there, because perhaps it fits better than equations do. Somewhere, in the vacuum between Mars and the Sun, an object older than the solar system itself exhales against the solar wind and feels no pushback. Its light, scattered across dust, travels millions of kilometers to reach our telescopes. It arrives not as an answer, but as a reminder that the universe is perfectly capable of surprising us, even with something as small as a speck of dust caught in sunlight. Every atom that shines tells a story. When the light of 3I Atlas was split into its spectral colours, the story that emerged was unlike any comet ever studied. The fingerprints of nickel gleamed bright and insistent, while iron, the usual companion of nickel in cosmic materials, was almost missing. That imbalance alone would have been enough to stir curiosity, but then came a ratio that made the room go quiet. 8 parts carbon dioxide for every 1 part water vapour. A typical comet, even one formed in the outer darkness, carries more water than carbon dioxide. Water ice is plentiful, easy to make, and hard to destroy. It should dominate. To reverse that ratio means something extraordinary about where and how this object formed. Somewhere unimaginably cold, where carbon dioxide could freeze as easily as frost on a window pane, while water itself became brittle with the chill. In the silence of deep space, molecules remember their birthplaces, their abundances, their isotopic balances. They are fossils of temperature and pressure. So when the European and American observatories compared their data, what they found hinted at a cradle far beyond the reach of any normal star's warmth. Perhaps a system adrift between suns, perhaps a circumstellar cloud that never fully formed a star. Nickel without iron raised a separate puzzle. These two elements are forged together in the cores of stars and supernova, where nuclear fusion arranges matter like notes in a chord. To separate them afterward takes chemistry, heat, and selective conditions found rarely if ever in nature. In the laboratories on Earth, refining pure nickel requires energy, catalysts, and time. In the cosmos, no known natural process should yield a composition so dominated by nickel lines while suppressing ions. Yet that is what the spectrum showed. Strong nickel emission bands, weak to vanishing iron. Some of the earliest analyses misinterpreted it as a calibration flaw. The James Webb spectrograph is sensitive enough that even a single photon misclassified can tilt results. But as confirmations came from ground telescopes using completely different instruments, the nickel signal persisted. This wasn't an illusion. It was a truth written in starlight. Scientists began to discuss condensation sequences, the order in which element solidifies a cloud of gas cools. Nickel condenses at slightly higher temperatures than iron. If 3I Atlas formed in an environment where cooling was unusually slow or chemically selective, perhaps nickel minerals could crystallize out while iron remained gaseous and escaped. That idea, though fragile, at least fits into known physics, yet it demands a setting rare enough to belong to only a few places in the galaxy. The cooling remnants of ancient stars, or the outskirts of protoplanetary disks chilled by distance and time. The spectral curve also showed faint traces of carbon monoxide, cyanide radicals, and something stranger, a faint shoulder of emission near wavelengths associated with nickel carbonyl compounds. On Earth, nickel tetracarbonyl is a manufactured gas, unstable and toxic, formed when nickel metal reacts with carbon monoxide under controlled conditions. It doesn't survive long in nature. Sunlight destroys it in minutes. The idea of it existing in open space sounds absurd. Yet the match was close enough to raise eyebrows. If the molecules are real, something must be continuously producing them. Otherwise, they'd be gone long before they reached the detectors. That's why some researchers described Atlas as chemically alive in a mechanical sense. Not biological, but active, reacting, generating compounds as though its interior were a slow, deliberate furnace. It's worth pausing on what that means. A comet's coma is usually a simple mixture of sublimated ice and dust. Frozen water, carbon dioxide, ammonia, perhaps a hint of methanol. The presence of complex carbonyl gases implies temperatures and pressures not typically found on the surface of small bodies. Deep inside, under layers of ice, perhaps chemical pockets form, where solar heating drives reactions between trapped gases and metal-rich rock. Those reactions could generate exotic molecules and release them through vents, creating the bright lines seen in spectra. Still, the absence of iron remains haunting. Without iron's presence, the nickel lines stand naked, too clean, too isolated. A natural object could in theory have such purity, but the probability is so low that some scientists quietly considered other possibilities. Artificial sorting, a product of processes unlike geology as we know it. For now, those thoughts stay confined to private correspondence and late-night meetings, where curiosity outweighs caution. The carbon dioxide dominance adds another layer of quiet unease. At an 8-to-1 ratio, Atlas behaves as though water ice was scarce or buried too deep to reach sunlight. Its outer layers might be crusted with carbon dioxide frost, forming a mirror-bright shell that reflects sunlight more efficiently than darker, dustier comets. That shell could also explain why the object remains cold. Carbon dioxide ice sublimates gently, carrying heat away without melting deeper layers. It becomes its own insulation, a natural form of thermal regulation. A comet from the outer solar system might show traces of such chemistry, but not to this degree. The only environments cold enough to sustain so much carbon dioxide ice are near the edge of the Oort cloud or beyond, regions that border interstellar space itself. Atlas, then, may not have formed near any star at all. It might be a relic of interstellar molecular clouds, preserved in vacuum since before our sun was born. It is humbling to think that we are watching the slow evaporation of material older than our solar system. Perhaps older than Earth's crust, perhaps untouched for billions of years. The molecules released by Atlas today began their journey long before humanity, before mammals, before the continents had settled into shape. Each spectroscopic line is a message across epochs, and yet, amid that quiet awe, there lingers an undercurrent of discomfort. Because the chemistry of Atlas doesn't only whisper of deep time, it also hints at deliberate order. Ratios that align too neatly, patterns too consistent to be chaos. Astrophysicists tread carefully here. The moment the data brushes against possibility beyond the natural, the conversation shifts tone, cautious and professional. But even in that restraint lies wonder. Perhaps the truth is simple. Perhaps we are witnessing a type of interstellar body we've never encountered before, a survivor from the primordial cold that drifted between stars since the galaxy's youth. Or perhaps it's something rarer still, a fragment of matter shaped by unknown physics, or, as some whisper, unknown intent. For now the light alone speaks. Nickel gleams where iron should. Carbon dioxide reigns where water sleeps, and the object remains cold, steady, quiet in its defiance. We may never know what drives that chemistry, but it continues to shine, drawing our instruments and imaginations toward it like moths to a silver flame. When light touches dust, it reveals secrets that even spectra cannot. For 3i Atlas, the dust itself has become one of the greatest enigmas of all. As sunlight scattered through its coma, the polarization of that light, the direction in which its waves vibrate, came back twisted, uneven, almost mischievous. Instruments aboard both Hubble and Webb confirmed it, and even the ground-based telescopes in Chile and Hawaii recorded the same whisper. This dust is not behaving like any known cometary grain. In ordinary comets, dust grains are tiny, compact, and roughly spherical. Their scattering of light follows well-understood rules. The degree of polarization changes smoothly with phase angle, the separation between sun, comet, and observer. But Atlas ignored those expectations. Its polarization curves spiked at strange angles, as though the grains were irregular, porous, or even hollow. Some observers described it as smoke-like, a veil of airy particles that drift rather than fall, floating in fields of their own making. The mathematics of such light behaviour suggests grains larger than expected, perhaps tens of micrometers across, yet with densities closer to soot than rock. That combination shouldn't exist in space for long. Solar radiation should blow away such fragile particles, or at least melt them into simpler forms, and yet the dust around Atlas persisted, glimmering faintly even weeks after major outburst had ceased. There is a particular kind of beauty in this. Picture it, an interstellar traveller surrounded by a thin luminous mist, dust shining softly, each speck rotating lazily, reflecting and refracting sunlight in all directions. From a distance, it must look like a halo of breath around a sleeping giant. The instruments record only brightness and polarization, but our minds add texture, silver ash suspended in darkness. Dust is a storyteller. Each grain carries within it clues to the conditions of its birth, the temperature, pressure, and chemistry that shaped it. In Atlas, those stories seem to contradict one another. Some grains show evidence of crystalline order, meaning they were once heated enough to melt and reform. Others are amorphous, frozen directly from vapour in deep cold. Together, they speak of an environment that swung between extremes, a place of both fire and frost. On Earth, we might find something similar in volcanic glass mixed with soot, but comets, those gentle wanderers of ice, are not born of volcanoes. So where does such contrast come from? One explanation involves impact shocks. When large bodies collide in the outer reaches of a stellar system, they can momentarily reach temperatures that melt rock and metal before cooling again into dust. If Atlas formed from debris of such an event, its composition could mix melted and unaltered material. Yet to preserve both extremes over billions of years requires isolation from any star's heat. Again, we return to the idea of deep interstellar origin, an object forged in violence and preserved in silence. The scattering behaviour of the dust also suggests something even rarer: alignment. Some particles appear to polarize light as though they share a common orientation, like tiny compasses pointing the same way. That can happen if magnetic fields thread through the coma, guiding the grains. We've observed similar effects around young stars and protoplanetary disks, where magnetic fields help shape new planets. To see it here, in a small interstellar visitor, is unsettling and wonderful. It means the dust is not random, it remembers direction. Astronomers using polarimetric instruments at the Atacama Large Millimeter Array tried to detect any faint magnetic signature that might accompany such alignment. The data were inconclusive, too faint, too far, but hints remain. Perhaps Atlas carries its own residual field, a relic of the place where it formed, frozen in for eons like a memory. There's also a stranger possibility. The porosity and reflectivity of the dust resemble materials humans use in advanced engineering. Foamed metals, aerogels, lightweight composites. Of course, to leap from resemblance to intent would be foolish. But the coincidence tickles the imagination. Particles structured like human inventions drifting naturally in space. Could the same physical laws lead both nature and technology to similar solutions? Lightweight strength, efficient scattering, stability across extremes. Perhaps the cosmos itself experiments with design. For scientists, the challenge lies in modelling how such dust can exist. Simulations show that if the grains were too porous, they would crumble under micro-collisions. If too dense, they would scatter light differently. To match the observed polarization curve, they must have the right balance. Structures intricate enough to trap light, yet open enough to remain light in mass. That balance is delicate, bordering on miraculous. Astrophysicists still debate whether this implies something unusual about the chemistry. Nickel-rich dust, as suggested by the spectra, might behave differently from silicate-based dust. Metallic surfaces could polarize light more strongly, enhancing the strange signals we see. If that's true, the dust could be a byproduct of vaporized nickel, condensing into hollow spheres as it cools, natural yet alien to anything found in our solar system. Whatever the cause, this smoke in the light, as one poet among the scientists called it, has become a focus of fascination. Dust grains too delicate to survive near the sun somehow persist, forming a whisper-thin shroud that defies time and heat. It reminds us that even the smallest things, the ones we cannot see without instruments, can rewrite what we know of the cosmos. Think about that for a moment. A few particles of dust smaller than a grain of salt drifting millions of kilometers from any world can teach us about the birth of stars, the structure of space, and the memory of magnetic fields. The universe hides its deepest wisdom in the most fragile of places. As Atlas continues on its path, the dust will thin, spreading along its orbit like a trail of faint silver smoke. Future observers may trace that line years from now, long after the comet itself has vanished from view, and in that fading shimmer they'll find data, proof that even across unimaginable distances light and matter remain in quiet conversation. We look at the numbers and the graphs, but what we're really watching is the dialogue between sunlight and dust, each photon a question, each reflection a reply, and 3 the Atlas. drifting through it all, keeps whispering back in patterns we are still learning to hear. We have gathered the fragments now, the glimmering threads that refuse to weave into a single tidy picture. Scientists speak of 7 anomalies, but it is really a feeling that unites them. The sensation of a familiar song played in a different key. Some notes still fit within the melody of comets. Others ring discordant, insisting that something deeper is hiding beneath the harmonies of nature. The first 4 we know well. The shifting size that refuses to stabilize. The jet that burns toward the sun instead of away. The chemistry that smells of nickel and carbon dioxide instead of water and dust. And the polarized grains that shimmer like smoke caught in sunlight. Each could perhaps be explained with patience, better data, a new model. Together they sound like questions, not answers. The remaining 3 are different. They live in the territory where numbers themselves seem to hesitate. The orbit, the timing, the physics of motion. These are not errors of measurement or chance. They are probabilities so low that to call them coincidence begins to feel like superstition. Let us drift through them gently. The orbit of 3i Atlas lies almost perfectly within the ecliptic plane, that thin, invisible disk where all our planets circle the sun. It is as if a wanderer from the stars has stepped neatly onto the only narrow path that all the worlds share. In the language of celestial mechanics, the odds of that alignment by random arrival are roughly 1 in 500. That is not impossible, but it is rare enough to raise eyebrows in observatories across the world. Interstellar objects should come from every angle, like raindrops falling on a pond. Yet this one skims the surface, riding the same flat water as Earth and Mars. The second permanent mystery is timing. The object's arrival corresponds almost perfectly with planetary positions that allow close approaches to Mars, then Venus, then Jupiter. The sequence reads like a map for efficient travel, the kind of route a spacecraft might use for gravity assists, saving energy by borrowing motion from the worlds it passes. The odds of such a trajectory appearing by accident are estimated at 1 in 20,000. Again, not 0, but small enough to make even cautious minds wonder. And the third anomaly, perhaps the strangest of all, the physics of motion itself. A comet that breathes out 150 kilograms of gas each second should recoil just a little, like the whisper of thrust from 1,000 invisible engines. The escaping gas should nudge the nucleus, changing its path ever so slightly. Every comet we have ever tracked behaves this way, but 3 Atlas does not. Despite its constant venting, it sails on as if anchored to an invisible thread. Newton's third law, action and reaction, seems to pause here, holding its breath. When the data first arrived, teams assumed their instruments were at fault. They recalibrated, rechecked, compared signals from different observatories. The conclusion was the same, almost 0 non-gravitational acceleration. The only natural explanation would be if the object's mass were enormous, tens of billions of tons compressed into a few kilometers, a small moon disguised as a comet. Yet that creates its own problem, because objects that massive should be vanishingly rare between the stars. It is in these paradoxes that science reveals its quiet courage. Researchers are trained to doubt, not to dream, and yet they must sometimes do both. Some speak carefully of statistical anomalies. Others allow themselves to imagine intent, not as certainty but as hypothesis, that perhaps we are witnessing the behaviour of something built, not born. The evidence does not yet demand that conclusion, but it keeps the conversation awake at night. In the offices of observatories, discussions stretch past midnight. Equations fill whiteboards, erased and rewritten as new data arrives. The debates are not only about physics but philosophy. How improbable must an event become before it earns a new category of explanation? At what point does persistence of anomaly become evidence of purpose? There is no agreed threshold, only a feeling, the sense that nature is whispering in a language we do not yet know how to translate. We have lived through such moments before. When the orbits of the planets first refused to match predictions, Newton gave us gravity. When the spectrum of hydrogen split into impossible lines, quantum theory followed. Each time an anomaly grew unbearable until it demanded a revolution of thought. Perhaps Atlas too is such a herald. Or perhaps it is a reminder that the universe remains free to surprise us, that not every riddle requires a new god to solve it. Even within these mysteries there is serenity. Watching from Earth, we see not chaos but elegance. A curve through space traced with precision, a slow ballet that defies probability but never beauty. The planets themselves seem to lean in, each one awaiting its turn to feel the faint passing of this stranger's gravity. Somewhere deep in its coma, gas continues to flow, particles drift outward, and light plays along their edges. Instruments record the faint signatures, spectral lines, shifts, reflections. We translate them into graphs, but behind those graphs lies wonder, the oldest human instinct. What is it? Why is it here? Could there be others like it, crossing through the dark unnoticed? Astrophysicists still debate whether these anomalies signal a new kind of natural object, perhaps fragments of disrupted planets, or frozen remnants from failed solar systems, or something far more deliberate. Each theory opens a different door into the universe's imagination, and through each door we glimpse the same thing: possibility. Tonight, as we drift beneath our own sky, those probabilities shimmer like constellations, 1 in 500, 1 in 20,000, 1 in 10 million. Numbers that seem cold on paper, but glow with meaning when you whisper them aloud, because even the rarest chance, given enough time, becomes inevitable somewhere. Perhaps that somewhere is now. Perhaps that is what 3i Atlas means, a statistical miracle written in starlight, challenging us to remember how small our certainties truly are. Imagine the solar system from far above, a delicate disk of light orbiting a quiet star. All the planets, moons and debris share roughly the same plane, an invisible sheet through space that astronomers call the ecliptic. For most of cosmic history, everything that enters this plane has been born from it. Rocks formed from dust around our sun, fragments spun from its early accretion disk. Now imagine a visitor from interstellar space, unconnected to our sun, arriving on a path so precise that it slides neatly into that narrow plane, tilted by only 5 degrees, as if following a hidden line already drawn through the dark. That is what 3i Atlas has done. Interstellar objects should arrive from all directions, random as raindrops. The galaxy's gravitational tides scatter them like seeds on the wind. Some fall steeply above the ecliptic, others plunge below, rarely grazing the same level where the planets travel. But Atlas is different. Its trajectory hugs the ecliptic, so precise that the probability of such alignment by pure chance is around 1 in 500. A small number, but not impossibly small, enough to trouble the sleep of the astronomers who calculated it. To understand why this matters, we can trace how such a path is measured. Each observation, a tiny pinpoint of light against the stars, defines a position in 3-dimensional space. Combine hundreds of these measurements and a pattern emerges, an ellipse, a parabola, or a hyperbola, depending on the energy of the orbit. For interstellar visitors, the path is hyperbolic, open-ended, meaning they will never return. But even an open path has orientation, tilt, and inclination. When those numbers mirror the geometry of the planets, curiosity follows close behind. Avi Loeb, whose name has echoed often in these discussions, once noted that if you were designing a probe to explore our solar system efficiently, you would send it on a trajectory like this, aligned with the planetary plane, intersecting key orbits in sequence. That alignment minimizes fuel use, allows gravitational assists, and makes close encounters predictable. Nature could do it, yes, but so could intention. And yet the universe rarely offers clean answers. The same alignment that feels deliberate might also emerge from a more subtle cause. Some models suggest that the galactic tide itself could nudge free-floating debris into shallow inclinations over billions of years, favouring those that happen to pass through the densely populated regions of stellar disks. In that view, Through-Eye Atlas is not unique by design, but by statistical gravity, drawn to our plane because it is where stars, planets and gas are concentrated. Still, this explanation does not soothe every question. If galactic tides favour shallow angles, we should already have seen many such aligned interstellar objects. Yet the first two, Oumuamua and Borisov, arrived at steep angles, plunging through our system like stones skipping off water. Why then does the third follow a path so neatly stitched to our own? The quiet answer might be coincidence. The louder one asks whether we are watching a pattern form in real time. 3 data points are not enough for certainty, but they are enough for wonder. From Mars, spacecraft have tracked the visitor's path with careful precision. The Mars Reconnaissance Orbiter, though built to photograph canyons and dust storms, now finds itself tracing a trajectory drawn across the void. Each frame of its high-resolution camera captures a point in the sky, a pixel containing centuries of motion. When those points are linked, the curve aligns almost perfectly with the Sun's equatorial plane. This geometry also creates something poetic. Every world in the inner solar system will share the same sunset with this object. When 3-Eye Atlas approaches its perihelion, its closest point to the Sun, the same sunlight will glance across Mercury, Venus, Earth and Mars, and then brush against its frozen surface. In that fleeting moment, every planet will cast a faint gravitational echo into its path. To visualize such alignment, imagine a thread stretched through the solar system. Each planet is a bead sliding along it. The thread itself is invisible, made of gravity and momentum. Atlas has found that thread, caught it, and follows it unerringly. Whether by chance or choice we cannot yet say, but the precision is beautiful. Astrophysicists often use inclination to describe this tilt. 0 degrees would mean perfect alignment with the ecliptic. 5 degrees, where Atlas sits, is small enough that the object crosses nearly the same regions of space as our own planets. This makes encounters possible, close passes where gravitational tugs exchange energy. It is these encounters that allow comets to shift their orbits, to fall inward or outward, to be captured or flung free. In planetary mission design, we call these gravity assists. Nature uses them to sculpt the paths of rocks and ice. Engineers use them to guide probes between worlds. Atlas seems to understand both arts. If it were indeed a probe, its designers would have chosen such an inclination deliberately. They might even time its entry so that its perihelion coincides with optimal alignment for planetary encounters, which, as we know, it does. The skeptic points out that coincidences multiply in a large enough universe. The believer notes that coincidence, repeated, begins to resemble intention. Between these two positions lies the quiet centre of science, where data waits for meaning. The alignment also has practical consequences for observation. Because the object lies near the ecliptic, it passes close to the glare of the Sun from Earth's perspective. That makes it difficult to track for long stretches. Later this month, it will vanish completely into solar brightness, hidden for nearly a month. Astronomers call this solar conjunction, and it happens to every planet in turn. But for Atlas, the timing feels theatrical. At the height of its mystery, it disappears. There is humility in these coincidences. The universe is vast enough that even rare events are guaranteed somewhere, sometime. Perhaps we were simply the lucky observers standing beneath the right sky. But even if it is luck, the beauty remains unchanged. When we look at that orbit drawn on our charts, a single curved line nearly overlapping the orbits of Mars and Venus, we are seeing more than coordinates. We are witnessing geometry as poetry, motion as music. The laws of celestial mechanics, written long before humans learned to read them, have guided this traveller along a path of quiet perfection. Whether this alignment whispers of design or destiny, it reminds us how precise the cosmos can be. In a universe that often feels chaotic, here is a thread of order so fine, so deliberate, it takes our breath away. And for now, that breathless silence is enough. Time and geometry dance together in ways that can seem almost personal. The orbit of 3i Atlas does not simply pass through the solar system. It moves with a rhythm that touches our worlds in sequence, like fingertips brushing across the keys of a slow piano. Mars, then Venus, then Jupiter. Each alignment arriving at just the right moment, each encounter needing only the smallest correction to become perfect. From a mathematical perspective, the probabilities behind this choreography are hauntingly small. For an interstellar object arriving at random, the odds of matching both plane and timing are roughly 1 in 20,000. The universe can certainly accommodate long odds, yet the pattern feels almost rehearsed. The arrival near Mars on October 3rd placed the object within 29 million kilometers, close enough for multiple orbiters to capture data. In July, it had passed a point that, with a nudge of less than 5 kilometers per second, could have brought it near Venus. And by March of next year, its path will skim close to Jupiter's gravitational field. It is as if the solar system itself were offering a sequence of invitations. We use similar alignments when planning interplanetary missions. The Voyager probes, the Pioneers, and New Horizons all relied on gravitational assists, slingshot maneuvers that trade momentum between spacecraft and planet. Engineers time these encounters with exquisite precision, calculating how each planet's motion can fling a probe toward the next. When viewed against that backdrop, 3i Atlas's trajectory resembles not a random interstellar flyby but an optimized itinerary. Still, caution whispers through every equation. We have seen patterns in clouds before and called them faces. The human mind is built to find order. Yet, there is also a quiet possibility that nature too composes such symmetries without needing our permission. Gravitational fields shape pathways of least resistance. Debris sliding along them might easily find efficient routes, much like water finding valleys carved by older rivers. Perhaps what seems deliberate is simply the echo of the universe's own economy, always using the easiest path through the maze of forces. Even so, the precision remains unsettling. It is not only where Atlas travels, but when. The arrival coincides with a moment in human history when our observation network is more complete than ever before. Telescopes on Earth, in orbit, around Mars, all awake and watching. If the object had passed even a decade earlier, much of its behaviour would have gone unseen. The timing feels theatrical, as though the curtain lifted precisely when the audience had gathered. We do not need conspiracy to find meaning in such coincidence. The universe often arranges its spectacles in silence, revealing them only when we are finally capable of noticing. Perhaps there are countless others that have come and gone, unobserved, each one leaving a thin, invisible trail of dust. But this one appeared in an era of awareness, an age of infrared eyes and digital patience. In that sense, the timing is perfect, not because it was planned, but because we were ready. Let's look more closely at what that timing reveals. When Atlas approached Mars, its relative velocity was about 60 kilometers per second, fast enough to cross from Earth to the Moon in under 7 minutes. Yet for planetary encounters, that is slow by interstellar standards. The first visitor, Oumuamua, raced past at 26 kilometers per second, barely staying long enough to notice. The second, Borisov, moved even faster. Atlas lingers. Its relative speed allows extended observation windows, gravitational interactions that accumulate over days instead of hours. If you were designing an interstellar reconnaissance craft, this would be the kind of approach you'd choose, close enough to observe, slow enough to adjust, fast enough to escape. But what if it is not reconnaissance at all? What if this object simply represents a class of interstellar debris that we are only now beginning to detect? Large, slow, dense wanderers that carry the fingerprints of their parent systems. Such objects could act as messengers from distant stars, each one a sample capsule of alien geology. Their trajectories would occasionally mimic purposeful design, simply because gravity's laws produce elegance whether intention exists or not. Even this natural explanation is thrilling. It means the galaxy is not empty between its suns. It is filled with travellers, orphaned planets, fractured moons, icy cores wandering endlessly. Our detection of 3 interstellar objects in such quick succession suggests the void may be busier than we imagined. Perhaps the spaces between stars are not deserts, but slow rivers, carrying the driftwood of creation from one shore to another. Still, 3i Atlas seems to move differently. Its path is not a simple sweep through our system, but a carefully curved arc. When plotted against time, its encounters align almost perfectly with our observational capabilities. Its perihelion, the point of closest approach to the Sun, will occur just as it passes behind the solar glare, unobservable from Earth. If one wanted to hide a maneuver or transformation, that would be the ideal window. By December, it will reappear, and astronomers will measure whether its velocity has changed. A single deviation from prediction, even a fraction of a percent, would be enough to transform speculation into astonishment. Until then, we watch and wait, tracing its curve through orbital charts like monks copying scripture. We compare each coordinate to the models, searching for the slightest deviation, and as we do, the thought lingers that perhaps our calculations are not the only ones being made. Time itself feels different when you think of such vast journeys. This object has crossed interstellar space for billions of years, indifferent to the spin of any single planet. Yet in these brief months, its fate and ours intersect. Our telescopes, our questions, our wonder, all aligned with its passage. Whether by accident or design, the meeting feels intimate. Astrophysicists still debate whether the trajectory's perfection can emerge naturally from known mechanisms. Some argue for resonant pathways shaped by galactic gravity. Others note that our sample size is too small to judge. But beyond the mathematics, there is emotion, the quiet awe of watching a piece of eternity pass close enough to measure. We are witnesses to geometry in motion, to timing that bridges billions of years with our single night of attention. The object moves on, silent and self-contained, crossing one orbit after another with impeccable grace. Perhaps it carries no message, perhaps it needs none. The message may simply be its path, a reminder that even in the vast indifference of the cosmos, precision still blooms like art. If there is one detail that has unsettled even the most composed of astronomers, it is this. 3i Atlas breaks the symmetry of motion itself. The object spews gas, vapour and dust into space, an act that should, by every law of mechanics, cause recoil. Every push demands a pull, every exhaust a counterforce, and yet the numbers show nothing. The comet exhales with the power of a storm and glides through space as if weightless, untouched by its own breath. It is as though Newton's third law simply forgot to apply here. For an ordinary comet, the mathematics is predictable. As sunlight warms the nucleus, jets of vapour erupt from sunlit fissures. Each jet exerts thrust, ever so slightly adjusting the orbit. Over weeks, that pressure shifts the path enough for astronomers to measure. These tiny changes are not errors, they are the fingerprints of real physics, measurable proof that momentum and energy remain in balance. But 3 Atlas, even while losing 150 kilograms of material every second, does not deviate at all. To sustain such stillness, its mass must be extraordinary, so great that the recoil from all that venting barely registers. Calculation suggests something like 33 billion tons. If the estimates of size hold, that would make the object denser than any natural cometary body we know, closer to solid iron than porous ice. But that cannot be true either. because the reflected light and temperature readings do not match any metallic surface, a contradiction suspended in silence. Some have compared it to firing a cannon made of mist. The powder flashes, the smoke curls, but the gun never moves. You can almost picture it. A small dark world venting gas through invisible pores, yet remaining perfectly poised, like a leaf floating on still water. There's a haunting calm to that image, the kind that makes data feel poetic. Engineers studying propulsion see echoes of a concept they call isotropic outgassing, an ideal state where gases escape evenly from all sides, cancelling their forces. In theory, such balance is possible, but only if the venting is perfectly symmetrical across the entire surface. In practice, comets are messy. Sunlight hits one hemisphere harder than the other. Gas pockets burst irregularly. Balance never lasts. Yet Atlas maintains it day after day. The probability of perfect isotropy occurring naturally is vanishingly small. It would be like flipping a coin 1,000,000 times and watching it land on its edge every single try. Still, nature surprises us. Perhaps its interior is porous, honeycombed with voids that channel vapour through an even distribution of vents. Maybe the outer shell conducts heat so uniformly that no side warms faster than another. But those explanations, while technically possible, demand an architecture of precision, an internal geometry that feels more engineered than accidental. A small group within the European Space Agency began running thermal models to test these ideas. When they simulated a spherical body with nickel-rich composition, they found that under certain conditions heat could distribute almost evenly through radiation and conduction alone. It was close, but not perfect. There should still have been a trace of acceleration, a subtle drift measurable in microarc seconds per day. Yet the real object's trajectory shows nothing. It's as if the universe has silenced motion itself around it. There's another strange detail. The shape of the outflow, measured through the faint tail brightness, shows no turbulence. In fluid dynamics, even the gentlest venting should create ripples, oscillations, or spiral structures in the dust. Telescopes sensitive enough to detect those patterns see instead a calm, laminar plume, like smoke in a room with no air. The gas leaves in perfect equilibrium, steady as breath through stillness. When data like this arrives, the language of science begins to sound almost spiritual. Words like balance, symmetry, harmony appear in research notes that usually deal only in numbers. Observers describe Atlas as poised, silent, unmoved. It is not just physics being tested here, it is our own sense of certainty. Astrophysicists have proposed several hypotheses. 1. The object's centre of mass might shift dynamically, redistributing momentum internally rather than through motion, something akin to gyroscopic stabilization. 2. The jets could be driven not by thermal evaporation, but by electrostatic or magnetic processes, releasing gas without significant thrust. 3. The gas flow might occur at velocities too low to impart meaningful reaction. Each explanation satisfies one piece of the puzzle, but contradicts another. None fit cleanly. Another theory drifts quietly among late-night discussions, that perhaps the material is not leaving at all. That what looks like outgassing might be light scattering off an active field, ionized particles caught in some stable magnetic lattice. In such a case, the object would not lose mass, and so there would be no recoil. It would only appear to vent, glowing softly while nothing truly escapes. Such a mechanism would be new to science, but not impossible under exotic conditions. If true, this could hint at a state of matter we've never encountered. A composite of metal and carbon dioxide behaving like a solid plasma. The sun's energy might excite it to radiate without motion, an optical illusion born from electromagnetic harmony. It's a fragile idea, but fragile ideas often lead to breakthroughs. Whatever the cause, the lack of acceleration places Atlas in a category of its own. Even Oumuamua, the enigmatic shard that first challenged our expectations showed a measurable non-gravitational push, tiny but real. Atlas's refusal to move has turned that earlier anomaly inside out. One accelerated without visible thrust, this one vents with none. They're opposites, bookends to a mystery we do not yet know how to name. For now, scientists can only measure and marvel. The trajectory remains steady, following its hyperbolic curve through the solar system, indifferent to the laws it seems to bend. Each day it sheds material and light but not momentum. Each night our instruments watch, waiting for even the smallest deviation that might confirm it is still part of the same physics we know. Sometimes in quiet moments, one wonders if the stillness itself is the message, that perhaps the lesson of Atlas is not in its behaviour, but in our reaction, how quickly our minds reach beyond what is known, how naturally we imagine agency in the face of perfection. In a universe ruled by motion, something perfectly motionless becomes sacred. If Atlas has taught us anything so far, it is that silence can be data too. A motionless comet, a recoil that never comes, a whisper of gas in a sea of vacuum, vanishing without consequence, and us, standing here, listening to a law of nature holding its breath. Among the many strange discoveries surrounding 3 Atlas, one has unsettled chemists more than any other. In the faint breath of gas drifting around this object, a spectral pattern appears again and again, a narrow set of absorption lines that perfectly match those of a compound once considered purely industrial, something never found in nature, nickel tetracarbonyl. On Earth this gas is both remarkable and dangerous. It was first synthesized in the 19th century by the chemist Ludwig Mond, who discovered that when nickel metal meets carbon monoxide under specific pressure and temperature, they bind together into a volatile molecule. Nickel tetracarbonyl is transparent, highly toxic, and extremely fragile. A few minutes of sunlight destroy it completely, breaking it back into its simpler parts. In laboratories, it is handled with fear and precision, used to purify nickel by allowing the gas to deposit pure metal when heated. In industry, it has been called both a miracle of chemistry and a ghost of poison. To find its spectral twin in interstellar space feels impossible. The conditions required to form it, relatively high pressure, controlled temperature, and a source of both nickel and carbon monoxide, are not typical of vacuum environments. In the cold emptiness between worlds, there are no containers, no stable surfaces, and little protection from radiation. Yet the emission lines from 3I Atlas trace precisely to the molecule's electronic transitions. The match is too good to dismiss as coincidence. The first team to suggest it was cautious, almost embarrassed. They published their findings as nickel-carbonyl-like compounds detected in 3I Atlas spectrum, carefully hedging their claim. But later analyses strengthened the case. When the object's light passed through its own coma, the spectrometers aboard the James Webb Space Telescope caught not just nickel's atomic glow, but the characteristic vibrational features of the carbonyl bond, carbon monoxide molecules attached to metal atoms in symmetrical clusters. What does it mean for such chemistry to exist in space? If it is truly nickel tetracarbonyl, then something must be generating it continuously. The sun's ultraviolet light would tear those molecules apart within hours. To replenish them, 3I Atlas must be producing them faster than they decay, an ongoing reaction taking place somewhere on or within the object. That, in turn, suggests an active process, not just the passive release of ancient ices. There are, of course, natural ways such a reaction could occur. Deep inside, carbon monoxide trapped in frozen pockets could be warming, reacting with nickel-bearing minerals to produce small bursts of the gas. As it escapes, it would quickly photodissociate, but constant venting could maintain the observed signature. This explanation is tidy, plausible, and comforting. Yet it assumes conditions of temperature and pressure that contradict the object's measured coldness. So the question lingers: How does something so cold create a gas that should require warmth and confinement? Some researchers suggest the reaction could take place within microcavities, where sunlight penetrates translucent ice and focuses energy like a lens. Inside such pockets, temperature could briefly rise enough to ignite the chemistry. In that view, Atlas becomes a vast laboratory of natural catalysis, where sunlight, metal, and carbon monoxide dance through ephemeral experiments. Others consider a more unsettling possibility, that the molecule is being produced not by heat but by energy fields. In plasma physics, ion interactions can mimic the effects of temperature, rearranging electrons without raising bulk heat. If Atlas carries magnetic or electrostatic fields, they might sustain reactions that create these compounds even in deep cold. But among scientists who study astrobiology and cosmic chemistry, there is another, quieter conversation. Nickel tetracarbonyl, they note, is one of the few metal organic molecules known to be useful in manufacturing, used to refine and shape metals with extreme precision. Finding it naturally would be extraordinary. Finding it in abundance near an object already marked by other impossibilities feels deliberate. No one dares to say artificial outright in their papers, but the question echoes between the lines. Could an advanced civilization, long vanished, have seeded or constructed objects like this? Devices that still produce chemical signatures as byproducts of whatever they once did? Could these interstellar visitors be the remains of forgotten tools? Machines fossilized into cometary form? It is a question too large to answer and too bold to dismiss. So for now, the language remains careful. Chemical disequilibrium, non-thermal production, unknown catalytic mechanism. Words that mean we do not know. The deeper mystery lies in the persistence of the gas. Even weeks after the object began its approach to the inner solar system, the signature has not faded. If it were truly a transient chemical, sunlight should have erased it long ago. Instead, its presence grows stronger near perihelion, suggesting a source that intensifies under solar flux. It almost behaves like an engineered system responding to input. Heat increases, activity rises, output stabilizes. If that were the case, then what purpose could such chemistry serve? Nickel tetracarbonyl decomposes easily into pure nickel when heated, releasing carbon monoxide. In industrial processes, that property allows precise metal coating or purification. In the cold of space, such a mechanism could theoretically deposit thin metallic films, perhaps for thermal shielding, perhaps for maintenance of surface integrity. Of course, that is speculation built atop speculation, but even the faint resemblance captures the imagination. For the cautious scientist, it may be enough to say this: 3 Atlas demonstrates a form of complex chemistry we have never before observed beyond Earth. It is a reminder that even the smallest molecule can carry mystery as vast as the stars. When you picture it, imagine a black body gliding through sunlight, surrounded by a faint mist of invisible gas, its surface whispering chemical equations older than our species. Each photon that strikes it ignites a molecule's brief existence. A flicker of life in the void. The gas drifts outward, decays, is reborn again. A quiet, endless cycle. Whatever its origin, that strange nickel breath has become a symbol for this entire investigation. Beautiful, inexplicable, and perfectly balanced between wonder and doubt. It is the scent of the unknown carried on starlight. Every discovery about 3I Atlas seems to echo itself, deepening rather than resolving. The chemistry spoke of nickel and carbonyls. Now the dust adds another layer, a mirror that returns our gaze. When the scattered light was analysed, it showed something uncanny. The grains drifting from the object looked less like natural comet dust, and more like the residue of combustion, as if some process had left behind tiny glassy spheres of fused carbon and metal. Under most telescopes, cometary dust reflects light softly, with a reddish hue that comes from silicates and organic tars. But Atlas's dust gleamed silver-grey, its spectrum unusually flat. To the naked eye it would appear almost metallic. The polarization curves, those subtle measurements of how light's direction changes, showed patterns unlike any other comet ever recorded. They suggested particles that are not irregular clumps, but smooth, possibly layered. That word, layered, caught the attention of laboratory physicists. In microgravity experiments aboard the International Space Station, they have seen how fine metallic vapours condense into hollow spheres, thin-walled shells formed by surface tension. Such structures are rare in nature. They require precise energy conditions to form. In industry, they're known as microspheres, used for coatings and lightweight composites. In comets, they shouldn't exist at all. The optical behaviour of the Atlas dust matched that of such spheres almost perfectly. Their brightness across wavelengths indicated uniformity, grains of similar size and structure, not the random jumble expected from natural ejection. If that result holds true, it would mean that every particle leaving the surface has been processed into near-identical shapes. This doesn't have to mean intention. Natural processes can sculpt order from chaos. In volcanic plumes, ash particles of comparable size sort themselves as they rise, carried by currents that favour equilibrium. In planetary rings, collisions grind ice into consistent granules. Perhaps the same self-selection occurs here. Fragile grains shattered and sorted until only the most stable forms survive. Yet there is something haunting in the precision. Under spectroscopy, the dust's composition leaned heavily toward nickel oxides and carbon compounds. Exactly the byproducts one might expect if nickel tetracarbonyl were breaking apart near sunlight. It's as though the chemistry described in spectra now manifests physically in the dust. If that's true, the grains are not relics of ancient formation but fresh emissions, forged in the object's present activity. Each one could be a manufactured flake, born from reactions at the surface. Laboratories on Earth attempted to replicate the findings. At the Max Planck Institute, researchers vaporized mixtures of nickel and carbon dioxide under vacuum conditions, cooling them rapidly. The resulting dust was astonishingly similar to Atlas's, bright, fine, spherical, with strange magnetic properties. It clung to itself in long filaments when exposed to weak magnetic fields, forming structures reminiscent of spider silk. The scientists nicknamed it cosmic smoke. When the same materials were exposed to ultraviolet radiation, they began to darken and fragment, mimicking the dimming patterns seen in the comet's trail. Somehow, Atlas was producing this material continuously, sustaining a luminous haze that persisted against sunlight's decay. To the scientific mind, this is the real fascination, not the possibility of design, but the demonstration of chemistry at the boundary of chaos and order. The dust around Atlas might represent a bridge between inert matter and self-organizing systems. Its particles respond to light, magnetism, and heat with almost biological subtlety, clumping, separating, aligning. If we could study such material up close, we might learn how the earliest matter in the universe learned to organize itself, a step that may one day have led to life. And yet, not everyone reads the data so calmly. To some researchers, the resemblance to engineered materials feels uncanny. The reflective microspheres, the consistent grain size, the cohesive alignment, all familiar features of manufactured coatings and propulsion residues. One physicist described the pattern as too clean for accident. Another countered that in a cosmos with endless variation, even perfection must happen somewhere. There's humility in that argument. The cosmos, given enough time, will try every combination of its laws. Somewhere an asteroid will fracture into a perfect cube. Somewhere else an ice crystal will mirror a snowflake's symmetry exactly. Randomness stretched across eternity becomes design. Still, the aesthetic remains irresistible. When you imagine the object surrounded by that silvery mist, it's hard not to think of something breathing in rhythm with sunlight. The dust forms, gleams, and drifts outward in faint filaments. as though the comet were wrapped in threads of its own making. The light plays across them like silk in a slow breeze. Astronomers analysing the scattering data found something else, a faint polarization rotation, suggesting that the dust particles carry charge. If true, this could explain their alignment and stability. Charged grains interacting with solar wind can form organised patterns, spirals, ribbons, even concentric shells. We've seen similar phenomena in Saturn's rings, where electrostatic forces sculpt delicate ripples invisible to the eye. Perhaps 3i Atlas is performing a similar act on a smaller, more intricate scale. Such order, whether natural or not, transforms the way we think about comets. They're usually symbols of entropy, dirty snowballs shedding chaos as they near the sun. Atlas feels like the opposite, a mechanism for creation. Every wisp of dust it releases seems purposeful, as if it were weaving something from sunlight and cold. And the more we look, the more that feeling deepens. In long exposure images, the tail doesn't fray like those of other comets. It remains narrow, coherent, as though bound by invisible tension. That tension could be magnetic, or electrostatic, or something we don't yet understand. It could also be coincidence. But it's beautiful all the same, a silver line drawn through the void, a mark of quiet order on the canvas of chaos. As the object drifts onward, its dust continues to teach us humility. We may never know whether its perfection is deliberate or accidental, but in watching it, we glimpse the universe's capacity for elegance, the way even the simplest elements, nickel and carbon, can combine into something that looks almost intentional. Perhaps that's the lesson here. The line between nature and artifice is thinner than we imagine. The cosmos doesn't need designers to make it beautiful. It simply follows its own rules until beauty happens by default. In the pale gleam of Atlas's dust, we see those rules at their most graceful. A whisper of smoke, a shimmer of light, and a reminder that even the smallest particles can hold infinity. If you stare long enough at the light curve of 3i Atlas, you begin to feel something uncanny. The brightness never flickers. The rhythm never wavers. It is as if the object does not turn at all. Ordinary comets tumble. They spin, wobble, and precess as jets of gas erupt from their surfaces, pushing them in random directions. That motion produces characteristic changes in brightness, tiny pulses that reveal shape and rotation. Scientists use those variations like fingerprints, reconstructing how a nucleus turns in space. But with Atlas, the light curve is steady, not smooth in the sense of chaos averaged out, but perfectly constant, hour after hour, day after day. This means one of two things. Either the object's surface is uniformly bright in every direction, or it isn't rotating. Both are astonishing. If it truly does not rotate, then something has halted its spin, a feat that defies both physics and intuition. Most bodies in the solar system rotate because of their birth. Collisions, accretion, tidal influences all impart angular momentum. To stop that rotation entirely would require a precise counteracting torque, one that cancels motion without destroying the body. Nature does not usually bother with such symmetry. One might imagine friction from outgassing, gradually slowing rotation, the way a windmill eventually halts when the wind stops. But in comets, the opposite happens. Uneven outgassing accelerates spin, creating torque that destabilizes them over time. The famous Comet 67P, visited by the Rosetta mission, changed its rotation period measurably with every perihelion. The more it vented, the more it spun. For Atlas to remain motionless while actively shedding gas borders on the miraculous. Perhaps the rotation is hidden, aligned so that we view the object directly along its spin axis, giving the illusion of stillness. It's possible, yes, but the odds are low. To maintain such a perfect orientation for months would require a coincidence of geometry that strains belief. The alternative is that Atlas spins, but but every point on its surface looks the same, reflecting light identically from every angle. That would demand a level of uniformity unknown among natural objects. Even planets, with their clouds and continents, show fluctuation. Only polished spheres or active energy emissions can maintain such constancy. When telescopes track the object, they measure not only brightness, but polarization, the direction of a light's electric field. In rotating comets, polarization drifts rhythmically as dust clouds shift, but for Atlas, it remains fixed, as though space itself were holding its breath around it. Some astronomers have begun to describe its behavior as isotropic serenity. The phrase is poetic, but it fits. Isotropic means uniform in every direction. Serenity describes the emotional effect of realizing that uniformity. It is not simply stable, it is still in a way that feels deliberate. The absence of rotation invites strange questions. Could it be tidally locked to something unseen? There is nothing nearby massive enough to exert such influence. Could it have internal gyroscopic stabilization, like the spinning wheels used in spacecraft to maintain orientation? Impossible, unless we abandon the assumption that it is inert. And yet, even within conventional physics, there might be clues. Some theories of interstellar matter propose that certain compact objects, like dense aggregates of metallic grains bound by electrostatic forces, can dissipate angular momentum efficiently through internal friction. In that case, 3I Atlas might be less a solid rock and more a clump of interlocking particles behaving like a fluid in slow motion. Over time, micro-vibrations could have drained away its spin, leaving it adrift in calm equilibrium. If so, we may be seeing an entirely new class of cosmic object, a self-damping aggregate, neither solid nor gaseous, balancing itself against the stresses of sunlight and radiation. But such an object would also explain the even outgassing, the balanced jets, and the motionless trajectory. It could be both flexible and stable, a paradox made tangible. Even so, the metaphor is irresistible. A visitor from another star wrapped in its own halo, turning not at all, facing every direction equally. It drifts through our system like a mirror held up to the cosmos, showing us how motionless true motion can appear. Astronomers at the European Southern Observatory ran simulations to see whether this steadiness might result from observational error. What if the object were rotating too slowly for us to detect, say, once every few months? That would flatten the light curve enough to seem constant. But over time, even a slow spin should shift surface features enough to change spectral absorption lines. Yet those two remain fixed. Whatever face Atlas shows us, it is the same face every day. That eerie steadiness led to philosophical musings. One astrophysicist wrote privately, "If this is natural, then nature has found a way to sculpt stillness." The phrase circulated quietly, becoming shorthand among researchers for anything inexplicable yet tranquil. There's a deeper implication too. Without rotation, the temperature gradient across the object becomes extreme. The sunward side should bake while the far side freezes to absolute darkness. Yet thermal readings from infrared observations show almost uniform temperatures, varying by less than 20 degrees. Something, somehow, redistributes the heat. It could be the venting itself, gas carrying energy around the body, smoothing differences like breath across glass. Or it could be a sign of active regulation, a process within that keeps balance against sunlight's assault. Either way, the object maintains its composure, refusing both spin and heat. When light from the sun strikes it, it does not flare brighter or dim. It simply endures. Its tail remains steady, its jets unchanging, its brightness constant. To watch its curve over weeks is to see a line so flat that the human mind, accustomed to noise, begins to sense silence. It's easy to anthropomorphize such perfection. Some call it patience, others design, others equilibrium. But maybe it is something simpler, a natural demonstration of balance beyond our understanding. If we listen quietly enough, perhaps this stillness speaks a truth we've forgotten. That motion is not the only sign of life. That sometimes the universe reveals its vitality through composure, and that in the deep hush of interstellar space, the most extraordinary act is to remain perfectly still while everything else spins. If 3i Atlas were merely still, that would be mystery enough. But it is also cold, too cold. By every law of physics, an object so near the sun should be awake with heat. Instead, it glides through sunlight as if made of shadow. Infrared readings show that Atlas absorbs gigawatts of solar power, yet radiates almost none of it back. A typical comet warms as it approaches the sun, its surface heating until buried ice begins to sublimate. But Atlas refuses. Even as it exhales gas and dust, its skin remains just above the freezing point of carbon dioxide, far lower than expected for its distance. If you were to stand upon its surface, the light would be blinding. The sun would shine 20 times brighter than on Mars, filling the sky with gold, and yet the ground beneath your feet would crunch like dry ice, cold enough to crack metal. It's an image that feels impossible. Fire overhead, frost underfoot. Scientists first suspected an error. Maybe the instrument calibrations were off, or perhaps the bright halo surrounding the comet masked its true temperature. But repeated observations from Webb, from Hubble, and from the Mars orbiters all confirm the same numbers. Atlas absorbs heat, and then, somehow, loses it. It's tempting to imagine a natural explanation. Perhaps the outer layers are unusually reflective, made of fine metallic dust that bounces sunlight away before it can sink in. A high albedo could keep the surface cool, just as polar snow reflects warmth on Earth. But the albedo of Atlas isn't especially high. In fact, it's rather typical. The light it reflects explains only part of the missing energy. The rest vanishes. So where does that heat go? Some researchers propose a network of subsurface channels like veins beneath an icy crust. As sunlight strikes, gas trapped inside could expand, carrying heat away through invisible vents before it builds up. In that model, Atlas acts like a self-cooling engine, bleeding energy into space through gas flows so even they leave no net thrust. It's elegant and consistent with its balanced outgassing. But to maintain that stability, the structure within must be intricate and vast, something far beyond the porous rubble typical of comets. Another idea borrows from quantum physics. Certain exotic materials can store energy not as heat, but as internal vibrations of their lattice structures, phonons trapped within the atomic web. If Atlas's nickel-rich composition allows such behavior, it might be absorbing solar energy and holding it deep inside, releasing it only as faint, undetectable infrared whispers. That would make it the cosmic equivalent of a thermal battery. Still, there's something disquieting about how precise its thermal balance seems. Its temperature doesn't drift. Even as it moves closer to the sun, gaining nearly double the energy flux, the readings remain constant within a few degrees. No known comet behaves this way. Natural systems lag, fluctuate, overshoot. Atlas holds steady, as though controlled by feedback, a thermostat written into ice. The European Space Agency team described the phenomenon as active thermal regulation. It was meant metaphorically, of course, but the phrase lingered in reports. It suggested intelligence, even if none was intended. Some of the data from the trace gas orbiter show faint periodic fluctuations in emitted light, too small to be seen in the overall brightness but visible in spectra. Every 18 hours, a subtle modulation passes through the signal, not random, not continuous, but rhythmic. The cause remains unknown. It could be resonance within the jets, or a reflection artifact from the spacecraft's rotation. Or it could be the pulse of a system adjusting itself, opening and closing invisible pathways of heat. There's another layer to the puzzle. Despite its low temperature, Atlas shows little water vapor in its coma. The CO2 dominates, with almost no H2O detected. Yet water is usually the main carrier of heat away from a comet's surface. Its absence means something else is taking over that role. Perhaps the nickel carbonyls we've seen, or perhaps another compound not yet identified. Whatever the mechanism, it seems remarkably efficient. In the quiet halls of observatories, conversations have turned philosophical. How can an object be both so violent in activity and so serene in temperature? How can it glow so brightly without ever warming? These are the contradictions that keep scientists awake under artificial light, staring at graphs that refuse to yield. Some imagine a deeper explanation, one that reaches into cosmology. Could Atlas represent a kind of matter that interacts differently with energy? Not dark matter, but a cousin, a hybrid state born in ancient conditions. There's a class of hypothetical particles called axions that could convert electromagnetic energy into invisible radiation. If such particles exist, they could drain heat directly into the vacuum, leaving an object cold even in sunlight. It's speculative, bordering on fantastical, but so is everything about Atlas. Whether the cause is physics or design, the effect is haunting. It turns the comet into a paradox of fire and frost, brilliant, active, yet frozen in poise. Observers describe its infrared images as ghostly, the body nearly invisible while the halo glows faintly around it, like a candle's breath seen through frost. If we are witnessing natural balance, it is one of the most graceful mechanisms ever found in the cosmos. If it is something else, we may be glimpsing technology older than our species, a way of managing heat in the vacuum that even our best spacecraft can only dream of. But perhaps there's no need to leap to the extraordinary. The universe is full of quiet efficiencies. Stars fuse hydrogen with 99.9% precision. Pulsars spin for eons with atomic steadiness. Black holes erase disorder behind their horizons. Against such company, a self-cooling comet hardly feels impossible. Still, the beauty of Atlas lies in its composure. It drifts through fire without melting, exhales gas without recoil, glows without heat. A paradox in motion, yet somehow at peace. If there is intelligence at work, it may simply be the intelligence of the cosmos itself. The same intelligence that shapes symmetry from chaos, that carved galaxies into spirals, that set every law of nature humming in tune. And as it moves closer to the sun, refusing to burn, we can almost feel that intelligence watching back through the faint shimmer of cold light. When strange data meets silence, the air in laboratories begins to change. Researchers lower their voices, emails grow more cautious, words like impossible start appearing between the lines of internal reports. That is where the story of 3i Atlas now sits, in the quiet tension between open science and the creeping sense that some questions are safer unasked. 2 days before the Mars flyby, an anonymous message appeared online, written with the dry tone of someone exhausted by verification. It claimed to come from a member of the European Space Agency's working group on interstellar objects. The post wasn't wild speculation. It contained technical details, spectral line values, telemetry references, things that fit uncomfortably well with data already public. The message said that the group had failed to make the object fit into any known category of natural celestial body. Not struggled, not debated, but failed. It described weeks of meetings where the same numbers circled the table, landing always on contradiction, outgassing without recoil, synthetic chemistry without a source, density too high for ice, too low for metal. The post's author wrote that they had begun to experience what they called professional cognitive dissonance. To believe the instruments was to disbelieve their training. To hold to natural explanations was to suspect that the data itself was lying. Neither option felt safe. In science, silence can be protective. Publicly, agencies maintain conservative language, awaiting confirmation. Further study needed. It's the sensible shield against premature claims. But privately, silence sometimes hides bewilderment. It lets the work continue without inviting storms of speculation. The leak broke that silence. at least for a moment. And what it described was a community divided not by belief in aliens or disbelief, but by exhaustion, the kind that comes when every attempt at reconciliation makes the paradox worse. Imagine standing before a blackboard covered in equations, each correct on its own, yet collectively nonsensical. You erase one term, fix a constant, try again. The sum still refuses to balance. That's the situation those scientists seem to face. Every adjustment makes another part of the model collapse, one astronomer interviewed off record compared it to looking at a reflection that keeps turning into a window. You can't decide whether you're seeing yourself or something on the other side. Even within large institutions, this kind of fracture isn't rare. The discovery of pulsars in 1967 went through a similar phase. When Jocelyn Bell Burnell first noticed the repeating radio signal, her team half-jokingly labelled it LGM-1. Little Green Men 1. They didn't believe it was alien, they just had no better placeholder. It took months to realise they'd found a rotating neutron star. History is full of such stumbles between wonder and caution. The scientists studying Atlas are not fools, they're caretakers of reason staring into a mirror that distorts. The leak described internal pressure to preserve the comet narrative. One quoted line read, "This position is no longer tenable, and the silence from leadership is becoming a serious issue." Another complained of data access limits. Not a ban, just endless delays. Data sets pending calibration. Models awaiting review. Slow suffocation by procedure. To outsiders, that might sound conspiratorial. Inside, it's mundane bureaucracy doing what bureaucracy does best. Stall uncertainty until certainty appears. The problem is, certainty has not appeared. A few independent researchers attempted to replicate ESA's results, using public archives from Webb and Hubble. Their reanalysis confirmed at least some anomalies: the nickel line intensities, the polarization ratios, the near absence of water. But when asked if that meant Atlas was artificial, they declined to speculate. Science, after all, is built not on belief, but on patience. Still, there's a quiet question lingering in the background. How long can patience last when every observation deepens the unease? At Harvard, Avi Loeb's group has pushed the boundaries of that patience. They've proposed frameworks to classify interstellar anomalies on a rule to 10 scale, not to sensationalize but to make discussion possible. In that system, Atlas rates a 6, a position of sustained uncertainty, where conventional explanations are still possible but no longer comfortable. Some critics accuse Loeb of courting publicity, of drawing connections where none exist. Yet his intent at its core seems simple: to make curiosity permissible again, to remind us that science progresses not by defending answers but by asking better questions. The Insider's post echoed that same fatigue. "It feels," they wrote, "like we are standing in a locked room with walls made of our own equations." A poetic sentence, maybe too poetic for an engineer, but the feeling rings true. Every field reaches moments where its language can no longer hold what the universe is saying. If the post was genuine, and no one can prove it, it gives voice to a universal tension. How do we protect credibility while facing the possibility that our models are incomplete? How do we invite wonder without abandoning rigour? Perhaps that's what they meant by silence protocol. Not censorship, but containment, a mutual agreement to keep awe quiet until it can be expressed safely in numbers. Yet silence also isolates. It leaves those wrestling with the unknown to do so in private, and in that quiet, the imagination begins to wander. It wonders what kind of object could release synthetic compounds, maintain constant temperature, and move as though balanced on a thread. The human mind doesn't like blanks. It fills them. For some, Atlas becomes a laboratory for new physics. For others, it becomes a machine, a messenger, or a relic. The truth might be none of these, but we reach for metaphors because they give the dark a shape. There's a tenderness in that too. The scientist's frustration, their restraint, their refusal to leap too soon. It all comes from love of truth, from reverence for data even when it hurts. So when we speak of leaks and insiders, maybe we should hear not rebellion but confession. The whisper of someone who has stared too long at a mystery and needs to share its weight. Whether the object turns out to be a comet, a relic, or something stranger, one thing is certain. It has revealed not only the limits of our instruments, but the limits of our composure. The universe, in its calm indifference, keeps reminding us that knowledge is never finished. And sometimes, in the hush of a control room or the glow of a monitor, silence is not suppression. It's the sound of minds recalibrating to wonder. When physics begins to dream, it conjures shapes that never cooled into matter. The leaked message hinted at one of them, a relic not of rock or ice, but of the universe's first trembling heartbeat, a thing called a cue ball. The name sounds playful, almost small, yet the idea is immense. A cue ball, in theoretical physics, is a stable knot of quantum fields, a sphere of energy bound not by solid matter, but by mathematics itself. It could be as tiny as an atom, or as large as a mountain, depending on how the early universe folded its fabric during the first seconds after the Big Bang. In those newborn moments, everything was fluid. Forces we now treat as separate, electromagnetism, the strong and weak nuclear forces, even gravity, were still blurred into one. As the cosmos expanded and cooled, that unity fractured. Matter condensed, radiation streamed outward, and quantum fields began to settle into their present states. But transitions in nature are rarely perfect. When water freezes, it can trap bubbles. When the universe solidified from energy into matter, it might have trapped tiny pockets of its original state, bubbles of unbroken symmetry. The equations predict that some of these bubbles could remain stable indefinitely, sealed off from time. Those are cue balls, leftover seeds of the earliest physics, wandering unnoticed through space. No one has ever observed one. They are for now only ghosts of mathematics. But their predicted behaviour is strange enough to explain the unexplainable. A cue ball would be enormously dense, perhaps as massive as a small moon packed into the space of a mountain. Yet it would not collapse like a black hole, because the pressure inside is evenly distributed, balanced by the fields that sustain it. It would emit a slow, steady trickle of energy as those fields decayed, converting primordial charge into particles and radiation. That decay could last for billions of years, a faint whisper of power continuing long after the stars that birthed it had gone cold. To an outside observer, such an object might look inert. No magnetic field, no rotation, no thermal spikes. Just a dark core surrounded by whatever matter had collected around it. Over eons, interstellar dust and ice could coat it like a scab, disguising the ancient engine within. And if such an object ever drifted into a planetary system, it would behave almost exactly like 3 Atlas. Its inner decay would warm the crust from beneath, causing gases to vent in all directions without recoil. The balance of energy would be perfect, action and reaction cancelling in a symmetrical bloom. From a distance, it would appear to be outgassing violently, yet moving serenely along its orbit. Its surface chemistry would be exotic, shaped not by the sun but by the particle cascade seeping outward from the core. Nickel tetracarbonyl, for instance, could form naturally under those conditions, carbon monoxide molecules binding with metallic nickel under sustained radiation. On Earth, we make it in refineries. In a cue ball's halo, nature might do the same by accident. Even its temperature would make sense. A cue ball's decay rate is constant. The energy leaving its heart is steady, neither rising nor falling with sunlight. The crust would regulate itself automatically, glowing faintly in the infrared yet never warming past its equilibrium. To call it a machine would be a misunderstanding. It would not have been built, it would have survived. An artifact of cosmic evolution, older than galaxies, operating on principles deeper than chemistry. Physicists once proposed cue balls as possible constituents of dark matter, the unseen mass that outweighs visible stars by a factor of 5. If such objects drift through interstellar space in abundance, they might explain the gravitational scaffolding that shapes the universe. Most would remain hidden, cold and silent, but occasionally one might intersect a solar system. To us, it would look like a comet behaving all wrong. Some astrophysicists find this hypothesis intoxicating. It bridges two mysteries with one idea: the strangeness of Atlas and the riddle of dark matter. Others find it too neat, too poetic. The mathematics behind cue balls depends on speculative versions of supersymmetry, a theory for which the Large Hadron Collider has yet to find any evidence. Without that foundation, the entire structure floats like mist. Still, the coincidences are difficult to ignore. The estimated density of Atlas, inferred from its recoilless jets, matches the lower bounds predicted for macroscopic cue balls. The isotropic gas emissions match their expected decay pattern. Even the faint spectral anomalies, the nickel without iron, the cold dust glowing softly, could fit the signature of a core slowly leaking energy. To imagine this is to imagine an object not born of star or planet, but of time itself. A relic from when the cosmos was a single quivering field of energy, a bubble that never popped. If that's true, then our telescopes have caught sight not of alien engineering, but of physics older than the stars. A survivor from the first microsecond of existence, drifting unnoticed through epochs, indifferent to suns and civilizations alike. Picture it: a dark sphere wrapped in ancient frost, the last ember of a different universe gliding silently through ours. Its decay, slow as eternity, creates just enough warmth to mimic life, to outguess, to shimmer, to whisper chemical illusions. Perhaps such objects are everywhere. Perhaps the galaxy is laced with these sleeping seeds, invisible in the dark but revealed when one drifts too close to the light. Each would be a message from creation, not written in words, but in equations. And yet, even that thought brings us back to the same humility. We don't know. The cue ball hypothesis might dissolve like mist under better data. But the dream it carries, that the universe still hides undiscovered forms of matter, ancient and self-sustaining, is too beautiful to dismiss. As one researcher put it, if Atlas is a cue ball, it is not alive, but it is awake. In a way, that's enough. For when we stare at its slow, cold pulse, we might be staring at the heartbeat of the cosmos itself, a memory of the beginning still breathing in the dark. If the idea of a cue ball sounds like a cosmic fairy tale, it is at least one that science knows how to test. The hypothesis is not built on faith alone. It carries predictions, clear and falsifiable, waiting quietly in the light of observation. The first prediction is simple but profound. If 3i Atlas hides an internal energy source, something decaying or radiating from within, then its brightness and its outgassing should remain steady, even as it drifts away from the sun. A normal comet lives by sunlight. Its behavior follows distance like a heartbeat follows breath. As the comet approaches the sun, ice warms, vaporizes, and forms a halo. As it recedes, the activity fades. The pattern is universal, written in the inverse square of light. But if Atlas continues to vent gas at the same furious rate after perihelion, when solar power should have dropped sharply, then something deeper is driving it. That test will come soon. When it re-emerges in December, telescopes will measure its brightness every night, tracing the curve of light against the curve of distance. If the two drift apart, if the comet refuses to dim, then sunlight is no longer in charge. The second prediction points not to brightness, but to energy. A cue ball, according to theory, releases its stored charge through exotic particle decay. That decay should produce high-energy radiation, not invisible light but in gamma rays and X-rays, wavelengths that reveal violence invisible to ordinary telescopes. If those signals are there, the detectors aboard the Fermi Gamma Ray Space Telescope and ESA's Integral Observatory could find them. No natural comet has ever emitted gamma rays from within. The only sources that do are cosmic powerhouses, pulsars, magnetars, supernova remnants. If a quiet, cold object in the inner solar system began whispering gamma photons, it would mean we're seeing something far stranger than ice and rock. To make these predictions testable is to give them vulnerability, and that is what makes science beautiful. Even the wildest speculation can be pinned to the sky and judged by light. Astronomers have already mapped out the observation plan. In early December, the Vera Rubin Observatory in Chile will resume its nightly sky survey, recording the comet's path against millions of background stars. Photometric sensors will chart any deviation in brightness. At the same time, radio and high-energy observatories will listen for signals. A cue ball should not care about sunlight, but it should care about time. Its internal decay rate would remain constant, a slow conversion of primordial energy into matter. By measuring that steadiness, the quiet defiance of seasonal change, scientists can decide whether the laws we know are sufficient. There is even a third unofficial test whispered among the working group. Watch for symmetry. If Atlas is truly isotropic, its coma should expand evenly on all sides, regardless of direction. Most comets develop tails shaped by solar wind. They lean away from the sun like streaming hair. But Atlas's forward jet points sunward, and if that structure persists unchanged as it moves through different solar conditions, then something is maintaining it. Something immune to the push and pull of radiation pressure. The beauty of these predictions lies in their patience. They require no new technology, only careful watching. The cosmos has a way of testing itself. For all our instruments, there's still the element of waiting, the slow art of letting the universe answer in its own time. Astronomers call this passive observation, a discipline that feels almost monastic. Each night adds another faint dot of data. Each morning, the numbers are compared to models. Gradually a pattern emerges or refuses to. The notion that 3i Atlas might glow without sunlight touches something ancient in us. It recalls the myths of self-luminous stars, wanderers that burn with inner fire. In a sense, this could be true again. A relic from the beginning, still radiating its own memory. Gamma-ray observatories like Fermi detect photons with energies millions of times higher than visible light. They are the footprints of the most powerful events in the cosmos. If any of those photons can be traced back to Atlas, the conclusion will ripple through physics like a bell. But the data must be impeccable. Background radiation from the sun and cosmic rays can mimic faint signals. The analysis will take months. Perhaps nothing will appear. No gamma rays, no anomaly. Just the steady fade of a dying comet. That would be its own kind of beauty. The universe confirming its own rules. But perhaps the curve will flatten, the brightness refusing to drop, the object lingering in defiance of distance. Then the questions deepen. The cue ball hypothesis also makes a subtler forecast. If the core decays into ordinary particles, it should leave behind a faint halo of positrons or neutrinos, particles that barely touch matter. We lack the instruments to detect that directly, yet neutrino observatories like IceCube in Antarctica will quietly monitor for directional coincidences just in case. Even a hint of correlation would stir the scientific world. All of this will unfold slowly, like a tide advancing over months, and beneath it a quieter realization is forming that we are watching the scientific method stretch to its edge. The process is old. Observe, predict, test, refine. Yet it feels new when the data seem to whisper of physics born before the galaxies. Each prediction becomes an act of humility. We do not declare, we listen. In that way, 3 Atlas has already served its purpose, whatever it turns out to be. It has forced us to remember that every law is provisional, every truth a reflection of the instruments we hold. The universe is under no obligation to fit our equations. When the December nights arrive, the telescopes will wake again, their domes turning like slow petals toward the dawn. Somewhere in the noise perhaps will be the answer, a light that fades as expected, or one that does not fade at all. And if it does not, then the oldest question in science returns. What exactly is shining out there, and why does it not obey the sun? Soon, the object will vanish. For 26 days, 3i Atlas will slip behind the sun, hidden in brilliance. Astronomers call this period solar conjunction, that bright and dangerous window when our own star blinds every telescope. During conjunction, even the best instruments on Earth and in orbit cannot look without risking their optics. The world's most sensitive eyes must close, leaving only imagination to keep watch. For ordinary comets, this disappearance is routine. They dive toward the sun, flare in glory, then fade again as they swing outward. But Atlas is no ordinary comet. Its alignment, its chemistry, its stillness, all converge toward this moment of concealment. To some, the timing feels like coincidence. To others, it feels like punctuation, a deliberate pause in the cosmic script. Behind that curtain of light, anything could happen, and no one would see. If the object has secrets to keep, this is when it can whisper them in perfect privacy. Any course change, any omission, any act of transformation would be hidden within the sun's glare. When it re-emerges, we will measure where it went, compare the before and after, and only then know what transpired in the light too bright to observe. Solar conjunction has always carried an air of mystery. Even planets vanish into it. Mercury and Venus pass behind the sun, becoming invisible until they reappear as morning stars. For a time, they cease to exist in human sight, their motions traced only by mathematics. It's a reminder that even in the age of constant surveillance, the cosmos still keeps moments to itself. The idea that 3i Atlas might use such a moment, intentionally or not, has become a quiet obsession among watchers. Because when something moves so precisely, with such perfect timing, one wonders whether coincidence has been stretched beyond its natural limit. If it were a natural body, this hidden interval would mean nothing more than a gap in data. But if it were a controlled craft, this would be its ideal chance to maneuver, to alter course, to release probes, to perform whatever adjustments its mission required without interference. Even the faintest burst of propulsion would be masked by solar radiation. No radar, no telescope, no spectrometer could see. Of course, such speculation is dangerous territory. Science does not assume intent, it only measures change, yet the mind can't help wondering. What would it mean for an interstellar traveller to arrive on such a perfect trajectory, align with planetary orbits, and then vanish behind the sun exactly at perihelion, the point of closest approach, when any manoeuvre would be most efficient? The coincidence is exquisite. To the more poetic among astronomers, it feels almost ceremonial, a curtain closing before the final act. The sun itself becomes both shield and stage light, illuminating and obscuring in the same breath. In the mythic imagination, this is the moment when the hero passes through fire to emerge transformed. In science, it is simply an inconvenient gap in data, but the resonance between the two is impossible to ignore. During those 26 days, observatories will not sleep. They will shift to indirect watching, studying how the solar corona reacts, how the solar wind patterns change. If Atlas releases material or alters its outflow, the sun might notice before we do. Its magnetic field briefly disturbed, its charged particles subtly deflected. Instruments aboard the Parker Solar Probe and the Solar Orbiter will quietly collect every hint. Meanwhile, on Mars, robotic observers will continue to monitor the sky for reflections. Even from that vantage, the sun's glare is overwhelming, but perhaps a glint, a pulse, a faint deviation might still appear in raw data. The human mind, hungry for narrative, will study every photon for meaning. History has its own rhythm in this regard. When Oumuamua passed behind the Sun in 2017, it too slipped away unseen for a while, and speculation filled the gap like water finding low ground. When it reappeared, its light curve told us it had changed shape, or at least its reflective surface had shifted. No one could say how. Atlas now approaches the same invisible passage, and again we will watch absence itself. There's a kind of humility in this enforced blindness. For all our instruments and equations, we remain creatures of shadow, dependent on what light allows. When light overwhelms, we see nothing. The sun, source of life, becomes the source of ignorance. It reminds us that perfect knowledge is still a myth, even in an age of data. Yet there is also something quietly sacred about that unobserved moment. The object will drift behind the sun, wrapped in radiance, untouched by human gaze. It will move through space as it has for eons, indifferent to our questions, continuing a story we cannot interrupt. That privacy, that unreachability, is part of what makes the cosmos beautiful. Not everything must be seen to be real. Still, when the days pass and the light begins to shift, telescopes will ready themselves like watchers at dawn. Engineers have scheduled the exact times of re-emergence, marking them on whiteboards in observatories across the world. In December, as the sun's glare finally eases, the first images will appear, tiny specks compared against old charts. Then comes the comparison, predicted position versus actual. If the coordinates align, then Atlas behaved naturally. If not, then the story deepens. A deviation of even a few arc-seconds could rewrite everything. It could mean a jet fired, a course shifted, a mass distribution changed. It could mean that during those 26 unobservable days, something happened that we missed. Until then, all we can do is wait. The silence of conjunction is total, and waiting is the hardest kind of science. It demands patience without expectation, curiosity without control. In the old days, before computers and radar, astronomers faced such silences often. They would record the last visible glimpse of a planet, calculate its hidden path by hand, and trust that the heavens would remain faithful. When the planet returned, there was relief, even gratitude. The universe had kept its promise. We find ourselves in that posture again now, watching a dark traveller vanish into the light, trusting that it will reappear where the equations say it should. But perhaps, deep down, a small part of us hopes it won't, that it will come back changed, carrying some new answer from behind the sun. Something to remind us that even the oldest star can still keep secrets. When 3 Atlas re-emerges from behind the sun, the world will already be waiting. Observatories will have been recalibrated, waiting like listeners on the edge of silence, ready for the first glint of motion to pierce the dawn. December skies will be short and cold, but every telescope on Earth that can see the ecliptic will turn toward the faint region where prediction says the visitor will appear. And in that first light, all questions will converge on a single point. Has it changed? The mathematics of orbital mechanics leaves little room for ambiguity. We know where 3i Atlas should be, the exact coordinates, to within fractions of a degree. If it appears there, unaltered in speed and brightness, then the mystery narrows. But if the object has shifted even by the width of a fingernail against the sky, then something must have acted on it while it hid behind the sun. Astronomers call this the return window, a kind of cosmic dawn. For weeks, they will measure parallax from different observatories, plotting new points against the old trajectory. They will look for deviations in its velocity, checking if it gained or lost energy, or if its angle has bent more than gravity alone could explain. Any deviation, however small, could reveal the presence of an internal force, propulsion, decay, or something else entirely. Meanwhile, the question of brightness will carry its own drama. If Atlas continues to glow at the same intensity despite its growing distance from the Sun, then the natural explanation fades further. The jets would have to be self-powered, driven by an energy source unaffected by sunlight. But if it dims, then the ordinary laws of physics remain in control, and the story may quietly return to the realm of comets and ice. Either way, December will be the reckoning month. The instruments aboard Mars orbiters will join in, watching from a vantage point nearly opposite Earth. Their data will help triangulate the trajectory, giving three-dimensional precision. On Earth, the European Southern Observatory's Very Large Telescope will perform deep spectroscopy, seeking any chemical shift, perhaps a change in nickel lines, or new gases emerging from the coma. Webb, positioned safely away from the Sun's glare, will collect infrared images that could reveal subtle structural changes, and in the background the Fermi Gamma Ray Space Telescope will continue its silent watch, scanning the region for high-energy photons. If the Q-ball hypothesis holds, a faint and steady gamma signature might appear now that the object has absorbed the Sun's full radiation. Nothing has been detected yet, but the instruments are patient. They were built for patience. Some scientists have proposed another test: Mars orbit itself. If the object's mass is truly as vast as 33 billion tons, its close pass could have left a measurable fingerprint in the planet's path. Even a microsecond of delay in Mars's orbital period might confirm its extraordinary density. It's a delicate measurement, but the gravitational dance between planets and interlopers leaves traces that precision radar can catch. ESA's ExoMars and NASA's MAVEN probes are already combing their telemetry for signs of such a tug. Then there is the Galileo project, still quietly gathering sky data on unidentified aerial phenomena. Its algorithms scan for brief, transient anomalies, flashes, motion vectors, unexplained reflections. In the days after Atlas returns to visibility, they will comb their archives for anything unusual that coincides with its path. Perhaps nothing will appear, or perhaps a brief flicker will cross the atmosphere of Earth or Mars, timed too perfectly to ignore. But in the meantime, there will be a different kind of waiting, the waiting of the public. News headlines will flare for a day, fade, then flare again as rumours circle. The words artificial and probe will drift through online forums, mixing science with storytelling, data with dreams. Even among professionals, excitement will simmer beneath restraint. The cosmos has a way of rekindling hope, even when reason says to hold steady. If the trajectory remains perfect, some will say that gravity alone explains everything. Others will point to the improbability, the alignment, the isotropy, the silence, and suggest that even if natural, this object marks a new class of matter, a bridge between the physical and the speculative. In those December nights, when the sky clears after long clouds, you might picture the observatories scattered across Earth, Chilean deserts, Hawaiian peaks, the dry plateaus of Spain, each one tracking the same faint point. Above them, satellites drift in synchrony, capturing spectra across wavelengths. Across the globe, countless screens will show the same curve of light reappearing in the data. What will we feel in that moment? Relief if the path is ordinary, or if it is not. But either way, the feeling will be the same one that has followed humans for millennia, that trembling between certainty and mystery when the sky changes, and we realise how small our comprehension still is. It is possible that nothing dramatic will occur. The object may continue past perihelion unchanged, cooling gently as it glides toward Jupiter's orbit. It may fade into the black beyond, leaving us only equations and a lingering sense of wonder. Science often ends not with revelation, but with a quiet, incomplete answer. Perhaps that is the truest kind. And yet, if it returns different, if its brightness holds, or its path diverges, or if gamma rays whisper faintly from its wake, then history will turn a page. It will mean that the sun has witnessed a conversation we were not invited to hear. Whatever happens, Astronomers know this much. By spring, the data will speak. The spacecraft orbiting Mars, the spectrometers in Chile, the gamma detectors circling Earth, all will compare notes, forming a tapestry of truth woven from photons and patience. And when the conclusions come, they will likely be cautious. Phrases like anomalous but consistent requires further study, non-standard energy mechanism, the language of awe wearing the clothes of restraint. But beneath that surface will pulse something older than science, the human instinct to look up and wonder whether the universe has just whispered back. For now, the visitor will sail onward, invisible to the naked eye, moving from the warmth of the sun toward the cool outskirts where Jupiter waits. We will keep watching, measuring, waiting for the faintest sign that the silence of conjunction left behind an echo. And as we wait, the cosmos waits with us, vast, unhurried, and utterly patient. Spring will come again, and with it, clarity. The dust of speculation will settle into data, and the light from 3i Atlas will thin into something more measurable, a fading streak of mathematics across the heavens. By then, the object will be gliding between Mars and Jupiter, still following its long open arc away from the Sun, heading for the quiet edges of the solar system. From the desert observatories, astronomers will gather in the cool night air to review their final sets of readings. The results will not shout answers, they will whisper possibilities. The trajectory may show no measurable deviation at all, or it may reveal the smallest, gentlest bend, a fraction of a degree, so subtle that one could almost dismiss it. The brightness might decline as distance grows or hold steady, defying the expected dimming. The numbers could go either way, but whichever path the data takes, something has changed in us. For now, the great experiment continues. The European Space Agency, NASA, and countless independent observatories will compare all the fragments: Mars orbiter imagery, spectral logs, infrared curves, particle counts. Juno, orbiting Jupiter, will add its piece, scanning for perturbations in the gas giant's magnetosphere as the object passes nearby. It's unlikely any one measurement will hold revelation, but together they form a mosaic of quiet truths. If Atlas remains exactly on its predicted path, then the story becomes one of precision, a cosmic coincidence so perfect it challenges probability, yet still natural. The universe, after all, has infinite chances to rehearse its miracles. But if the path diverges, even slightly, the world will lean closer. Because then we would be witnessing something active, a conversation between matter and will, between the physical and the unknown. The difference between those two outcomes, natural or not, might lie within margins smaller than dust. A deviation of a few meters per second over millions of kilometers, a fractional change in the slope of a light curve. Science is patient with such subtleties. The truth of a universe often hides in decimals. And what if the object fades, leaving no proof either way? That too is an answer. The cosmos does not owe us resolution. It only invites participation. Our role is not to master it, but to listen long enough to notice when it whispers. Perhaps the lesson of 3i Atlas will not be about extraterrestrial design or exotic matter, but about humility, about how small our certainty still is, even after centuries of looking upward. Some nights, as the data stream quiets, you might imagine the object itself, a dark ember moving outward, trailing faint silver threads of dust, gliding into the colder reaches where sunlight turns thin and the solar wind grows tired. Out there, in the spaces between the orbits of planets, light has time to rest. Every grain of dust it sheds will drift for centuries, orbiting in silence, becoming part of the faint glow we call zodiacal light. The dust of the solar system, the breath of visitors long departed. Astronomers will continue to chase its memory for years. The models will refine, the instruments will improve, and perhaps another object like it will appear. Each one will bring its own strangeness, a new puzzle wrapped in familiar light. Over time, patterns may emerge, and the line between the extraordinary and the natural may blur into something larger and more elegant than either word can describe. What remains certain is this: 3 Atlas has already changed us, not by revelation, but by invitation. It reminded us that even in an age of precision and data, the sky can still surprise, still humble, still feel vast enough to hold mystery. That a beam of starlight, crossing billions of years, can land on an instrument built by fragile hands and whisper, "There is more." And so, we end as we began, beneath the same velvet dome of night, the same stars that have watched every generation look up and wonder. The interstellar visitor will fade beyond sight, but its echo will remain, hidden in the margins of equations and the quiet awe that fills observatories when the lights go dim. Maybe one day another will follow. Maybe this was only the first of many. Or maybe it was something rarer, a single message drifting through space, carried not by design but by chance, asking us to remember that the universe is still alive with possibility. In the stillness of those spring nights, as we close the shutters and end the measurements, one truth feels clear: we have been visited not just by an object, but by a question. It has moved through our system, through our minds, and now moves on, leaving wonder in its wake. Perhaps that is all the cosmos ever meant to send. And now, as the instruments fall silent and the data fade into archives, let's drift together for a moment in the hush that follows discovery. Imagine the vastness above, that quiet sea of stars, each one shining from so far away that its light has aged more than any human story. The visitor has gone, but its path lingers, a faint curve through space, marked only by memory and mathematics. We can almost see it still, moving slowly outward, its dust settling into the deep dark between planets. Around it stretches eternity, calm and cold and endlessly patient. In that distance, everything slows, the galaxies breathe, ancient photons cross the black in unhurried waves. Somewhere beyond our sight, other wanderers drift between suns, carrying fragments of time older than we can name. The universe holds them all without judgment, without haste. Take a breath with it now. Let the pace of stars set your rhythm, steady, slow, as if the cosmos itself were breathing beside you. The questions we've asked tonight will wait. The answers will come, in their own time. The sky will still be there tomorrow and the night after that. The same constellations, the same slow pulse of light across infinity. All we have to do is look and listen, and let wonder do its quiet work. So rest your thoughts. Let the mystery be what it is: vast, unfinished, beautiful. The universe keeps its own kind of lullaby, written in starlight and silence. And as you drift towards sleep, know that you are part of it too. A small, bright consciousness under an endless sky, sharing in the same ancient calm.